Mic check. Hello. Hello, mic check. Hello, mic check. Mic check. Mic check. Mic check. Hello.
So after this, after introduction, you just open them. You know that, right?
Please be seated. Good morning, one and all. Welcome to the day 2 of the 2-day national workshop on hydrogen fuel technologies and future trends, organized by Alliance University and IISc Bangalore under the aegis of CIIS. We are starting the technical session by the backbone of CIIS, Dr. V.K. Saraswat, Chairman of CIIS and Honorable Member Niti Aayog. And we are honored to have his session as the first technical session of today. And he was benevolent enough to do the technical session to all the participants who are present here. Thank you so much, sir. Over to you, sir.
Where is my laptop? No, sir.
No, I don't want this. My laptop I want here. You're a fantastic fellow. No, give me my laptop, that's all. If you can do it, fine. That's what I asked them. You have the cable coming here?
No, sir, directly to you.
It's okay. I can change. No problem. I need to change the script. I'll do that. So very good morning. And after yesterday's full great session all of you had, I could also see the glimpses of a few sessions which went off very well. And Alliance team has done a great job because they have collected all the relevant points from each lecture. And the Vice Chancellor showed me some of it. I'm really very happy to see that excellent coordination is being done in this particular case. So, yesterday I talked to you about my experiences with hydrogen, right from my childhood to as a rocket scientist and also as a policy maker in NITI Aayog. I also mentioned to you the kind of momentum.
Hello.
No, it's okay. Are you able to hear me? Not yet. Okay. Today I'm going to talk to you about specifically, because I gave you the idea why this workshop or conference was planned. Because when I'm taking a review in NITI Aayog of what is the kind of progress India has made towards making hydrogen as an alternate fuel for mobility, transportation and stationary power generation, I found that the depth to which the research is required to be done, both in terms of modifications in the existing IC engines or developing new IC engines for hydrogen related operation or developing specific fuel cells for using hydrogen for generating power. The kind of work which was going on, it was more superficial to the extent of whatever is happening in the foreign countries, we were just trying to put a layer on top of that and trying to bring it to the market. So I felt that there's a need for us to revive our research portfolio in such a manner that we study the fundamentals of hydrogen combustion, all the aspects which are related to modifications required in the IC engines for use of hydrogen as an alternate fuel. So that's how I said, let's bring all the scientists and technologists together and have this workshop. And happy that Alliance University came forward, and that's why we are today. When I look at the energy transition strategy of our country, we find that there is a need for us to look at every aspect of use and production of energy for what we call as net carbon zero or net zero by 2070. So in NITI Aayog, along with various departments, the strategy was worked out. And this slide indicates what all has to be done to reach net carbon zero. Yesterday I mentioned to you that one of the major requirements is to take stock of who are the biggest polluters in terms of the greenhouse gas emissions. So we found that one of the highest producer of greenhouse gas emission is the power sector. Then comes the transport sector. And then comes the industry. Rest all are small. So these are the three giants which are actually responsible for adding carbon dioxide or the greenhouse gas emissions which are affecting the climate. So the strategy was to start looking at each one of them, and first thing was industry decarbonization. Why we thought industry decarbonization? Because it is linked directly to the economic value, what each industry runs on the basis of profit. If you introduce any modifications, and those modifications are going to affect the profit or the competitiveness of the industry, then there's a major problem. So industry decarbonization was thought of as one of the major criteria. When we looked at the power sector, we realized that whatever you do, renewables you will bring, you will have very clean biomass, energy based and things like that. But with the growing demand of energy in the country, which is expected in terms of numbers, if I want to share with you, that by 2030, our demand could reach as much as 900 gigawatts. So if we are to look at that, obviously we cannot wish away the use of thermal power plants. And hence coal becomes a very important fuel. So if the coal is to be used, and coal is a polluting fuel, so we said we should go for clean coal technologies. Clean coal technologies are such that instead of doing combustion, you do gasification, or you do certain other processes like carbon capture, utilization and storage, which is mentioned, or operate the thermal power plants at very high efficiency, like earlier we used to have subcritical power plants where the steam temperature would not be more than 500 degrees. Then we came to supercritical power plants, the steam temperature went to 540 degrees. Then we went to ultra supercritical power plant, the steam temperature went to as high as 600 and all. And today we are talking of advanced ultra supercritical, where we are talking of 720, 740, depending upon the kind of materials what you have running the turbine. So this clean coal technology requires improvement in the thermal efficiency of the power plants, thereby reducing the emissions and reducing the demand of coal for producing the same quantity of the same amount of power. So CCT is that. Then came CCUS, the clean coal, carbon capture and utilization. So whosoever is polluting, whether it is a cement plant or a steel plant or a refinery or thermal power plant, if we can capture the carbon dioxide from there and utilize for production of minerals, production of chemicals, production of various other products, making fuels out of it, then you can reduce the impact on the environment. Another method is storage, because the amount of carbon dioxide which you are putting in the atmosphere is so high that we cannot utilize it all the time. So there is a need for us to go for storage. And storage is that you should be able to inject the carbon dioxide into aquifers, basalt rocks and so on, so that they remain there for thousands of years. So this is another technology which was thought of. In the terms of mobility, when it came down, we thought we should start looking at cleaner alternate fuels. Because petrol, diesel, fossil fuels have been there and they have been polluting. All of us know, right from particulate, what we call as the criteria pollutants to particulate matter to carbon dioxide, everything. So then we thought ethanol, ammonia, these are some of the alternate fuels which have been identified, which are cleaner, that if you burn them compared to diesel or petrol, you get less greenhouse gas emissions. For example, if you burn methanol, you don't get any particulate matter at all, and so on. Then we said for the power generation, renewables should be one of the major sources, because that is supposed to be the least polluting. In the alternate fuels, hydrogen was also identified as one of the cleanest fuel, and everybody talked that hydrogen is the fuel of the future. We should certainly work for that. But when we came down to renewables, except for the bioenergy, whether it is the wind power or it is the solar power, all of them have a major problem with respect to the uncertainty of its availability in the time of the day, the month, in the year, and so on, based upon the vagaries of day and time and climate. That means you need to support the renewables something which will provide the base load power. And base load power is important because there is a phase difference between the peak demand of electricity versus the peak availability of power. And because of that, you need base load power. And in that sense, we said that the nuclear power should be one of our major portfolio for supporting that. Because nuclear power is something a plant runs for 60 to 80 years on a constant load, and even you can turn down. The turn down ratios of the nuclear plants are also quite good. In addition to doing this base load, a lot of thoughts came out that whenever excess energy is there from the renewables, why don't you store that energy? And hence came the idea of battery storage systems and energy storage systems, whether it is pumped hydro system or battery storage or air storage or whatever that. And alongside, mobility became sustainable mobility. That you should be mobile, but you should not pollute. So that was sustainable mobility, the major charge. And when you introduce renewable power, which is generally DC, into the AC grids what we have, you need to do the grid management. So the smart grids came. Yesterday, I think, not yesterday, not during the conference, but I was discussing what are the problems we have today in introducing huge quantity of the renewable energy into the grid, which is the AC grid. And we are dependent on import of many of these items like controllers and so on from the foreign countries for maintaining the smart grid. So this is our problem. These are the areas, and in this area, the one element which is very, very important is the hydrogen as a fuel, and that's why this seminar today. If you look at the roadmap of the alternate fuels which have been tried out from very, for last many years, the history is that from 1994, we started talking about the dual fuels. Mr. Gadkari, he will always say we should have the buses running on ethanol as well as on diesel or petrol. So that was the era of dual fuels. Then people in 97 said, why not use CNG, compressed natural gas, which was this is less polluting. So 97, 99, it was CNG. Then people came out with the Italian solution that why don't you have a retrofit of LPG. I still remember a large number of people putting LPG cylinders in the Maruti 800 car. And the kit used to come from Italy and they used to connect. So, and that was the time when biogas also came. Then from 2010 onwards, we have started talking of not directly using hydrogen, but blending hydrogen with the CNG. Indian Oil Corporation first ran, I think 18% hydrogen in a CNG bus in Delhi, and it was a successful trial. 2016 onwards, it has been hybrids, that we should not only have battery, but we should have battery and IC engines together. Alongside, the blends are continuing because India took a policy of blending fuel into the existing petrol and diesel. So then came ethanol 85%, 20%, 5%, HCNG, and now we are all even talking of a derivative of methanol called the DME, which can be a direct replacement for diesel and so on. We also tightened our norms as far as the mobility is concerned. We talked of that BS3 should come to BS4, and now we are all at BS6. That means we are tightening the criteria as far as the pollutants are concerned. And now the next one is going to come is the BS7, which is going to happen. Once the gas came, the gas economy became predominant, and India also fell into the trap. Gas economy became predominant because America got the shale gas, and Europeans started getting gas from the Russian. So that was a system. So LNG and hydrogen and ethanol, and even we tried blending methanol with diesel and petrol and so on. So many experiments between 23, 24 have been done. Alongside, there has been a significant work which is being done now, 2025 and 30, on focusing on hydrogen as a fuel. Not that the work has not been done. Many people have tried running a hydrogen bus. Mr. Narayanan was talking yesterday, the bus which they ran along with Tata. You know, those are experiments which are called add-on experiments. But the basic thing is, very little has been done to use hydrogen as a fuel in the IC engines, and also even in the kind of fuel cells which we are using today. First of all is heavy dependence on import of all these items. And second thing is whether they have the future survivability possible because of the problem of availability of the critical minerals and materials which are required to produce these systems. So there is a strong benefit for using hydrogen in the road transport. There are no range anxiety. We are talking of electric vehicles. Yesterday we were saying, somebody said that a company has promised 500 kilometers, but it does not go beyond 250 kilometers. My own personal experience is in Niti Aayog. One car was promised to go to 120 kilometers and I could not reach Gurgaon. So that is a kind of problem. Short refueling time, lack of vibration, smooth driving experience. Environmental benefits are well known to you. No toxic tailpipe emissions, greenhouse gas reductions. Even they say because of certain reasons, the noise reduction is also there. And it will be in a position to comply with all the regulations with respect to the air quality and the carbon. So there are lots of benefits like enhanced energy security, effective storage solutions, creation of new local employment opportunities, because once you start this system, you will have new industry coming in. If you have to do the storage, a major industry on type 3, type 4 cylinders. If you go for transportation of hydrogen, you need hydrogen transport trailers and so on. So industry will come up with, will certainly have a major boost on the economic and competitiveness. A cleaner future for India through transport electrification and adoption of green hydrogen in industries. Now, what the other countries have done? If you see the global strategies and initiatives for hydrogen IC engines deployment, European Union has, as I was mentioning yesterday, already set the target of net carbon zero by 2050, not 2070. They are also working on research and innovation in hydrogen, and they have already set in place the regulatory framework for hydrogen infrastructure and safety standards. In fact, there is a relationship between European Union and IIT Delhi Energy Center on the safety standard for hydrogen. Many of you who are working in hydrogen, I think you should certainly get involved in that. United States certainly has a hydrogen and fuel cell technical advisory council. There is a hydrogen at scale, that is the motto they have. And they have been providing a lot of incentives to the industry for hydrogen infrastructure and development and focus on clean hydrogen. Yesterday we were talking of what is the right word to be used. This clean hydrogen has been adopted in US also. Fuel cell and vehicle deployment. India, we know, yesterday we talked about is our national hydrogen mission, where there is a focus on hydrogen fuel cells, use of hydrogen as an alternate fuel, liquid form or gas form, hydrogen, ammonia in IC engines. China has taken major initiatives. Focus on hydrogen as a part of the 14th five-year plan for them. Fuel cell vehicles are already coming there. Refueling stations are being set up. A lot of financial subsidies are being provided. Japan and Korea, Japan was the early mover in this area. They set up the hydrogen infrastructure for distribution, transportation, and production in very early stage. So there was a strategic shift from hydrocarbon, but they were importing hydrogen from wherever, and even today South Korea and Japan believe in that. But they were encouraging hydrogen IC engines for power generation and marine applications. Australia depends upon that they will produce hydrogen and export. So that is the kind of system they have. So each country has followed his own method. There is a history of hydrogen IC engines. Not that we are the first one. I don't know how many of you know that. Tangier Limited produced a town gas-based power generation system for marine application or for road applications or rail applications in 1906. There was no activity between 1970 and 2000, but man made the hydrogen IC engine city bus Berlin, 14 units between 2006 and 2009, 4 units operated till 2015. Between 2000 and 2012, there have been significant development. BMW luxury sedan was done. BMW hydrogen IC engine, 100 units were manufactured. GM Opel, they also did that. Japan anti-cell R&D 2005 and 10. Dutch projects were there in this period. Ford also did. So there was a major work which was done between these 12 years. 12 to 19, again not much of activity. But now 22 onwards, you can see on the right hand side how much work is being done. Hydrogen being used in JCBs, hydrogen in Isuzu, Volvo, Bosch, many of these things. So there is a significant amount of explosion. And many of the industry partners were there. Caterpillar was there yesterday. They were talking about hydrogen they have produced in their, not in India, but outside India. The process is simple. All of you know what we are talking of. You can have option that you can have liquid hydrogen or you can have gaseous hydrogen and directly inject. Some people are saying hydrogen injector, air, and the port directly inject and so on. So in this case, liquid hydrogen is stored in the cryogenic tank. A pump transfers hydrogen to an expansion chamber. Hydrogen gas is injected into the engine cylinder along with air, and hydrogen air mixture in the combustion chamber does the job. This is a simple explanation. Now, I think some experts are sitting here. Ravi is here, Chari is here, many of them who have worked in this area. There are hydrogen IC engine fuel injection technologies. First among them is the port injection spark ignition method at about 3 to 10 bar injection pressure, where in the intake, where the air intake is there, you inject the hydrogen and use a spark plug. Rest all remains same. Key challenges are the power density, abnormal combustion, efficiency is an issue. This is called generation 1. And these kind of things are by 2025 they can come in the market as a retrofit. It is the simplest system, these are the plus points, low cost fuel system. But then there are negatives for this, which is called the risk of backfire into the intake manifold, highly prone to pre-ignition, and the transient response in this case is quite poor. The second one is a direct injection spark ignition, which is done at the 10 to 50 bar, where intake is not touched, hydrogen is separately injected, and you use the spark plug. Generation 2 it is called, and we expect that this will come between 25 to 30. The advantage is that it can provide higher power density, improved efficiency and transient response. Again, the problem here is injection system with high durability is required. I am given to understand, I don't know, Ravi can explain to me, whether Bosch has developed a hydrogen or Westport has developed a specific hydrogen injection system now, injectors they have done. Yeah, I think so. Somewhat higher NOx emissions is a problem here. The high pressure, then the third generation which is coming, generation 2 plus as we call it, is instead of 10 to 50 bars, you inject at 100 to 600 bar. And pilot fuel or pre-chamber ignition. So that is a kind of explanation. You have air intake, you have exhaust, and you have direct injection with a pilot fuel and being done. High pressure pump is required in this case. NOx is a problem. Fuel compression energy, generation 2. So best efficiency you can get here. Power density is good, transient response is good, no backfire, reduced pre-ignition. But there is a residual pressure in the empty tank because the entire thing does not get exhausted. And there are a lot of work being done to optimize this pressure because I have given you a range between 100 to 600. Obviously, there has to be some optimum pressure at which it should be done. So these are the three major efforts other than the one work which is being done by Ravi is on the opposing piston type of configuration, where two pistons are used and no conventional combustion chamber. The pistons heads themselves form the combustion chamber in this case. You can have a single crankshaft, you can have a double crankshaft and inject it at that point in time. Generally, injection is done at the trailing part of the compression point so that you can reduce the NOx formation. And advantage of that, it is going to give you much better thermal efficiency compared to the three numbers what we have talked. I don't know whether there is a problem with respect to NOx in that case also, but certainly we have to take care of NOx by running it lean in some other manner. So I think India should, as the work is going on in ISC, should work on this opposing piston type of thing, and also people should go for direct injection at the earliest. Those industry partners who have already got the spark ignition engines running, I think they can try the port injection with the safety measures which are required for reducing the backfire. Typical modifications which you need to make in the engine architecture is given here. For example, the first line shows what is there, the diesel, common rail high pressure pump and injector, and of course turbocharging in some cases. In the case of hydrogen, you need multi-point fuel injection. A specific injector is required for that. Then throttle body, spark plugs, piston, coil and plug, depending upon what is the kind of a thing is there. So variable geometry turbocharger in a two-stage turbocharging system would be needed. Crankcase ventilation is very important for hydrogen concentration dilution. That is the major requirement. So one should design accordingly. These are some of the easy methods like what happens in the combustion chamber mixture of hydrogen powered ICs. The low ignition energy required, which is, that means hydrogen is easy to ignite. Wide flammability range, almost 4 to 75% volume percentage in air, allows very lean operation and improving efficiency and reducing the NOx. So that is the advantage. Some of the design measures to prevent pre-ignition is using cooled exhaust gas recirculation, EGR. I was discussing with some people yesterday. How many of you have tried EGR as a process for doing this prevention of pre-ignition and backfire? We have to optimize the ignition timing because, as I was mentioning to you, a lot depends upon at what point in time you have injected in the combustion stroke and at what point in time you have ignited. You can have direct injection or turbocharging. Because of the high temperature, I think we need high resistant valves and cylinder heads and also improved cooling systems. These are some of the requirements of the combustion chamber. So what are the major challenges in hydrogen IC engine? Lean combustion and turbocharging for maximizing the thermal efficiency. These are the requirements. Chamber design has to be done for better cooling, and gas exchange optimization has to be done. Performance can be done with the help of a two-stage charging and engine scaling, upsizing to meet the power demands. Fuel storage and supply, all of us discussed yesterday that fuel storage, it could be safety problem, so one has to be very careful in terms of onboard hydrogen leakage detection and sealing. You should have sensors to ensure that there are no accidents. High pressure hydrogen tank integration is required, because if you are going to use in the gaseous form, the ideal pressure is 350 to 700 bars, and hence you need to have very, very important sensing mechanisms and integration, because you can't inject at 700 bars. So you need pressure regulators, you need check valves, and the entire hydrogen injection system has to be designed accordingly. One good thing that has happened is the component technology as far as hydrogen handling is concerned, because of the rocketry, have developed worldwide very well now. The joints, the sealing joints, the weldability, the valves, the regulators, these components are industrially available, which are certified for use with hydrogen. So that is the advantage for those who are designing hydrogen systems. Emissions, after the treatment system for NOx mitigation, we have to go for ultra lean mixture or EGR and water injection. These are some of the emission reduction measures. Safety, I already mentioned to you, you have to adhere to standards like ISO, SAE for hydrogen. And in some cases, maybe hydrogen specific fire suppression systems also have to be incorporated. Then abnormal combustion, this is another challenge, one has to look at that in the case of direct injection. Many times if you don't control the injection point with the valve timings, the hydrogen detonation is a possibility, and you have to safeguard against. If you want to compare the performance of hydrogen engine versus a gasoline engine, in terms of thermal efficiency, hydrogen is 35 to 40, gasoline is 30%. Power output slightly lower due to the low volumetric energy density in a PFI mode, whereas gasoline is higher. Torque response, because of the high flame speed, it is much better and compared to the petrol. Emissions, zero CO2, negligible HCACO and low NOx, whereas petrol, all of you know what are the problems. Fuel storage requires high pressure tanks and engine durability, potentially longer due to the cleaner combustion. You don't have soot formation and things like that. Yesterday, I was talking to you about the use of hydrogen and what the Chinese have done. This is a slide which I made in 2017, where I proposed for heavy duty applications of fuel cells or the electric drive. Batteries are not the answer, but the fuel cells, and there the fuel cells should be run not on carrying hydrogen, but producing hydrogen on board and using a hydrogen derivative fuel like methanol. Why fuel cell? Because it is superior weight in terms of less weight for same energy, less greenhouse gas emissions, less capital input, and less well-to-wheel emissions, take less time to refuel. This diagram shows that there is a fuel here. After the fuel taken to a certain temperature, about 260 degrees. So it splits, and then you get carbon dioxide and hydrogen, and you separate carbon dioxide and take clean hydrogen. That is, and directly the clean hydrogen, which is about 99.99% clean, can be directly full on a fuel stack. Now, there is a lot of heat which is generated in that. So rejected heat can be used in a vapor absorption cycle or a heat pump, which can do cabin cooling or space heating. And of course, once the power is produced from the fuel cell, you can have the power conditioning and directly run an electric motor. Now, This practice has been adopted in China now. For a car, battery weight would be 60 kg, while methanol fuel cell will weigh only 18 kg. Carbon dioxide emissions from a fuel cell electric vehicle will be 2.7 grams per kilometer as compared to 20.9 grams per kilometer from an EV. Please see these differences. Methanol offers huge diversity and hence can work with IC engines and E drives, can be converted to electricity with an efficiency of 75%. Hydrogen from methanol can be produced by an onboard reformer, as I mentioned to you. This is for the students, how does a fuel cell operates. So you have a typical anode reaction, you have a cathode reaction, you have a NAT reaction, cathode anode on a fuel cell. Oxygen is put inside, hydrogen is from the other side, and then you get water as an output and you get electricity. I won't go into details of this. You can read it in your exam, in your classroom. So when you take comparison of fuel cells with the gasoline engines and electric motors, this is again very clearly glaring thing, their advantage. The hydrogen fuel cells efficiency is in the region of 50 to 60%. By the way, there is a lot of effort being done by the fuel cell community to improve the efficiency of the fuel cell to as high as 68 to 70%. But only solid oxide fuel cells, which are still in the development stage, this kind of a number is likely to be attacked. But in terms of PEM fuel cell, unless PEM fuel cells work on high temperature, more than 120 degrees, you will not be able to achieve higher efficiencies. Gasoline engine 25-30, but the battery of course is highly efficient, 85 to 90%. Emissions, water vapor and zero as far as battery is concerned. Refueling time is the most important criteria. As far as hydrogen content, 3 to 5 minutes. Gasoline is about 5 minutes and battery, all of you know, is minimum is 30 minutes. It could be as high as few hours. Energy density, high and low. Infrastructure, hydrogen, limited infrastructure needed. Gasoline, you know, the worldwide we have huge gasoline infrastructure in the country, and battery infrastructure also is growing. As I was mentioning yesterday, today we have almost about 1400 battery charging stations which have been set up across the country. Maintenance, low, only gasoline engines are high. The hydrogen IC engines and hydrogen fuel cells. Now this is a debate many people will have been doing. Why should you do IC engines when you have got only fuel cell? So these are some of the factors which can be considered. For example, efficiency, mid and high load, good. Excellent in the case of a fuel cell, low and mid load. Cooling needs, intermediate, but in the case of fuel cell, you need high, critical for stationary and slow moving applications. Emissions, we have a NOx problem in hydrogen. Durability is high. But as far as battery is concerned, it is improving with new R&D, but still there is a question mark. The batteries are sensitive to vibration, but not the hydrogen IC engines. The use of noble metal, that is the most important part which I have been telling. Critical minerals and materials in the case of battery is very high, whereas IC engines don't need all that. Fuel purity, it is tolerant to any kind of hydrogen purity, where the fuel cell, PEM fuel cell, if you have even 5 ppm of carbon monoxide or carbon dioxide, the fuel cells don't work. So you have a major problem. Upfront costs, IC engines are lower, fuel cells are very, very costly even today. Cold start, no issues, but there are major problems of starting as far as the batteries are concerned. Resale value, you know, we don't know as far as the batteries what will be the thing. So these are some of the features I thought I should discuss with you and give you. In terms of storage, there is a storage system design and space efficiency. As I was mentioning, physically you can have a compressed gas, you can have a cold or cryo compressed, or you can have liquid hydrogen. In case of materials, you can, yesterday I was talking to you about metal hydrides. So you have absorbents, metal MO5 kind of a thing. You can have liquid organic, methyl cyclopentane, interstitial hydrides, complex hydrides like sodium aluminum hydrides, and chemical hydrogen like ammonia and boron hydride and so on. So these are various, there's a lot of work going on the hydrides. The major problem, as I mentioned yesterday also, the energy required for decomposing the hydride to generate hydrogen is higher generally than the energy required for its formation. And that's the reason the research is still not able to solve this problem. For high pressure storage, this is a typical configuration of a high pressure cylinder with inner liner made out of high density polymer, any polymer, and the rest is carbon fiber composite. And the major design problem in this case is the integration of the metallic parts like the valves and all, which are shown in the blue line, and those things becomes a major problem. You can have different sizes and capacity. If you take atmospheric, then for the same amount, this is a size. If you take it in the form of ammonia, this is a size. If you take compressed air, this is a size, and if you get liquefied, this is a size. This is the kind of difference you can make out if you, when you make the choices with respect to the storage. Present status of hydrogen storage infrastructure in India. Somebody asked me this question, I think some press person was asking. Tata Steel became the first Indian company to develop hydrogen transportation pipes, hydrogen compliant API X65 pipes. 100% pure gaseous hydrogen at 100 bar they are doing. Inox CVA flagged off the largest bulk liquid hydrogen storage tank ever made in India with a capacity of 238 meter cube. Design has been done by South Korea. Cryogenic storage tank is built in European Union standards and requirements. IIITs and NITs are advancing metal hydride systems for efficient and safe hydrogen storage. For example, AB3 lanthanum, cerium and nickel, and AB2 titanium, zirconium and chromium alloys are thought of. There's a company called Vedasya. I think there are a lot of advertisement nowadays on the TV for this company. Designs and produces type 3 and type 4 composite overwrapped cylinders. So we don't have a problem. People should not think that India is not manufacturing the 700 bar cylinder. It is possible, but we need to set up the testing facility and infrastructure, and also the PESO has to set the standards as far as regulations are concerned. Otherwise, such a high pressure system cannot be let out in the market without proper regulatory mechanisms. Hydrogen fuel application in India. This is with respect to the National Hydrogen Mission. Deployed 37 hydrogen powered buses and trucks, 15 using fuel cells and 22 using hydrogen combustion. 9 hydrogen refueling stations have been placed. Vehicles will run on 10 different key routes like Delhi, Agra, Pune, Mumbai, Ahmedabad, Vadodara. 208 crore allocated for these pilot projects. Somebody was mentioning yesterday that Leh, we have hydrogen fuel cell buses operational at 11,500 feet. Mumbai, first hydrogen powered train to be launched in 2026. My friend Mahesh Rajpurohit is a railwayman. It is one opportunity where we can really remove all diesel engines and put hydrogen engines for running the railway system. Delhi and Gujarat and Kerala, they are all working in that direction. The scaling of hydrogen mobility comes with few challenges. One of the main problem is the infrastructure. As I mentioned to you, when Japan was introducing hydrogen, Japan being a small country, for them it was not difficult to set up charging stations and things like that. We are trialing 9 hydrogen stations, trailing behind Japan, which is 166, and Germany 105. But it requires a lot of investment. Heavy transport focus, 40% of the diesel buses can be replaced, but truck fuel costs must drop below, hydrogen should come to below $200 per kg to compete. Is this achievable by 2030? That is one of the major problems. So if you are not depending upon green hydrogen for IC engine applications, then I think this is achievable. But if you are only saying that I'll use only green hydrogen, then you have a serious problem in respect to timelines. Cost competitiveness, this number we discussed number of times. Green hydrogen in terms of rupees is anything between 320 to 400 rupees a kg. Grey is 120 to 160 rupees a kg. Electrolyzers, I mentioned, anything between $500 to $1,200 per kilowatt. This has to come down to less than $250 per kilowatt for viability. There's a global learning curve. California's 16,000 plus FCVs face hydrogen shortages. And Japan aims for 800,000 FCVs by 2030. But adoption challenges remain. India has to learn from these to avoid the setbacks. This is the major thing. Fuel cell efficiency, I mentioned to you. Hydrogen fuel cells offer greater than 600 kilometer range and fast refueling, but with an efficiency of 30 to 50% compared to battery electric vehicles, which gives you as high as 90% efficiency. Integrate the hydrogen fuel into power systems. That is, hydrogen as a long duration energy storage for balancing renewable power supply, especially in the isolated grids or remote regions. Enable hydrogen-ready gas turbines and fuel cells to generate electricity during peak demand or renewable intermittent. In fact, hydrogen to be used in the gas turbines, that also has to be looked at. Establish hydrogen fuel infrastructure. That is, encourage public-private partnership for setting up operating hydrogen refueling stations and create standard designs for high-pressure dispensing systems, because you have to compress on site. You can't be transporting 700 bars. You can't run the heavy duty vehicles. So railways and heavy duty vehicles ideal. Safety, very important. So for efficient hydrogen storage, support R&D in advanced storage materials like metal hydrides. I was mentioning to you yesterday carbon nanotubes and metal oxides. Create safety protocols and certified storage standards to gain public trust in hydrogen. So to conclude, what is the future outlook? Near-term decarbonization is feasible. Hydrogen IG engines are ideal for hard-to-electrify sectors like heavy trucks, rail and marine. Infrastructure compatibility leverages existing fueling stations and engine platforms. It is possible. Lower development costs, we have seen the 3 different configurations which I have given, not much of cost. Faster market adoption, familiar technology increases acceptance among the OEMs and fleet operators. If I tell now any of the IC engine companies like Kirloskar or Ashok Leyland or Caterpillar or others, I think they will have no difficulty in adopting to hydrogen IC engines. Even the diesel generator sets today, or which are running on the SI cycle, they can all be readily converted into hydrogen gensets. So you have smooth transition possible. Then comes fuel flexibility, can operate on blends using transition, like hydrogen and natural gas I mentioned to you. There has to be a key R&D focus for this community. I think it is important that you should have improved the direct hydrogen injection systems. I think a lot of work is required in that area. I mentioned to you optimize the pressure of injection, valve timings and so on and so forth. Reduce the NOx emissions without compromising efficiency. We can go leaner and leaner, but you still have an efficiency problem. Develop the lightweight, low-cost hydrogen storage. Enhance engine durability under high temperature conditions. In fact, one of the questions which is being raised often, that operating at high temperature, will it have an impact on durability? I personally believe, coming from the rocket background and also reusable rocket engines, it is not a problem. The right choice of the material and a good cooling system, you can have thousands of hours of running of the system. And optimize combustion strategies for various load conditions. This is very important. Part load to full load, what are the combustion strategies? And all the software guys who are sitting here, all the software engineering people, I think the good controller to maintain timings during the strokes and all that is a major software requirement to be developed along with the combustion scientists, and that is where this workshop should be in a position to actually take us to the right level of performance as far as hydrogen IC engines are concerned, fuel cells are concerned. But looking at what should be our priority, I would say hydrogen IC engine is our low-hanging fruit. So we should focus on that in a quick manner and be one of the topmost leader as far as hydrogen IC engines are concerned. Speed up the research work, bring the industry part of it, and also bring all the OEMs which are engaged in the IC engine manufacturing today as development partners so that your prototypes goes to the market at the earliest. Thank you very much. God bless you all.
Thank you very much, sir. Generally, we call Victory King in our RCIE. So, sir has done excellent presentation. And speaking after sir is like Suraj ko Deepak batane ki baat hai. So, I will not continue that one. So, if any question is there, we can go ahead. Otherwise, we will go to next session.
Yeah, ask questions. No problem. Anybody? Yeah, go ahead.
For producing hydrogen fuel, why the electrolyzer is used or why the only the electrolyzer? Because instead of that, why not the living microorganisms are used?
Why not?
Living microorganisms, because this hydrogen fuel are completely green gas now. The living microorganisms are capable of carbon arresting, crude oil engulfing. In aerobic means there are photosynthetic organisms are there which split the light, which use the source of light to split the water. And for salt water means there are halophilic bacteria, there are heat resistant bacteria. In anaerobic means there are some baseless species which have the hydrogenous enzymes to produce the hydrogen gas. Because some of the developing countries are using this organism for their future direction. Why India fails to value the importance of these microorganisms?
No, I think there's a misconception that India is not looking at microorganisms for production of hydrogen. As far as biomass-based hydrogen production is concerned, there is a very strong work which is going on use of different kinds of inoculums, whether it could be a microorganism or it could be a bacteria for biomethanation process. Biomethanation process does not require air, it's anaerobic. And in that case, you can take biogas and then you can separate out hydrogen. So this is, a lot of work has been done. And electrolyzer is one route because we know that we can split water and get hydrogen. But that is not the only route. Yesterday I mentioned to you that today hydrogen is being manufactured using gasification of coal, steam reforming of the natural gas. So these are all processes being used today. But only thing is each of these processes, including the bioacterial process, if you look at only the tailpipe kind of emission, it produces carbon dioxide. It is not that it is as green as electrolysis. So you understand? So in a strict sense of green hydrogen, electrolysis with renewable energy is the cleanest, or in my opinion, electrolysis or thermal decomposition of water using nuclear energy is the cleanest. That's why the name has come the pink hydrogen. The pink hydrogen is called from the nuclear energy. It comes the cleanest in form because the total emissions, right from the material to the tailpipe emissions, in the case of nuclear hydrogen production is 12 grams of carbon dioxide per kg of hydrogen. Whereas if you take solar energy based electrolytes, it is 38 grams of carbon dioxide. If you take bio is considered carbon negative, like microalgae, because we know that we are using biomass and the carbon dioxide which is coming, it will recycle by the atmosphere through the photosynthesis and you will have the the biomass again. So that's why it's called negative. But if you look at only the tailpipe emissions, then it is also producing carbon dioxide. That's the point.
Yes, sir. Thank you.
Sir, Sir,
Yeah,
that
who
was
else?
nice question and nice answer also. Sir, I have very simple question. And what is the expected lifetime and the maintenance requirement differences between hydrogen IC engines and conventional IC engines?
I think I talked about it.
But you mentioned the differences, but what expected lifetime, which is more?
I don't have a number to give you
Okay.
because hydrogen IC engines are very few available today. But looking at the point of operation and the kind of combustion products which are formed during the combustion of hydrogen, the cylinder which normally gets coated with soot and also runs into clogging of the exhaust pipes and so on, these problems are not there. I'm talking with respect to maintenance. Whether than diesel and petrol, all these problems are there. Second part is, as far as hydrogen is concerned, there are issues, but they are technically amenable. For example, there's a issue of temperature, as I mentioned to you, technically amenable. If I can manage the temperature, then durability will be high and no issue of maintenance. Another issue is lubrication. In the case of hydrogen IC engine, lubrication has to be done very, very carefully. Not much data is available on what kind of new lubricants are required to be used because of the high temperature and also the stability of the lubricant at those temperatures. So these are the issues that have to be addressed. But overall we can see that hydrogen IC engine will have better maintainability as compared to the other IC engines. Am I correct, Mr. Ravi? He is my guru, so I am asking him. Nobody else? Okay. Yeah, somebody.
So one small question, sir.
No, there's a lady there first. Preference to lady.
Thank you,
Yes,
sir.
madam.
Sir, we are actually a highly populated country. At present, we are using a gasoline, diesel as a common source for vehicles and all. And we are slowly converting our vehicle to battery engines and moving on. Now, we are trying to shift our ideas to hydrogen type fuel engines. Whether it is easy for a common people to handle these kind of fueled engines, whether it will be safer, because if it goes to common people, whether they were able to handle these kind of things.
As far as handling a hydrogen IC engine concerned, if adequate safety provisions have been made in the design and manufacturing and monitoring, as a user you have no problem. Whether you are having a diesel petrol IC engine or a hydrogen IC engine. When it comes down to battery, despite, I'm talking with respect to the experience of last 10 years, where the battery introduction has taken place. Despite many of the measures which have been taken to reduce accidents in the battery, the accidents are still taking place. India being a tropical country with temperature variations going from one end of the country at 55 to 58 degrees Celsius to as low as minus 20 degrees in Leh Ladakh, you have a very difficult problem to design battery system for this kind of a variation. So a battery may work beautifully in Bangalore because here minimum temperature to maximum temperature hardly varies in the summer to winter by about 20 degrees. But if you are Delhi, even in Delhi, we touch 48 many times. And we touch minus sometimes in some parts like Churu and all that, -1, -2 also. So we have a battery problem, and so far whatever work has been done on the battery development, some of these problems are still remaining to be solved. So it's a choice to be made. Where do you live? What is the size of the vehicle you have? And what is your daily usage? If your daily use is coming to office and going back home, driving not more than 100-120 kilometers a day, battery vehicle, small vehicle, in a climate which is not very adverse, absolutely the safest mode of transportation. But if you are looking for a heavy duty truck in the same conditions, it is not competitive, because a truck with a total weight of something like 12,000 kgs, the battery will weigh about 4,000 kgs. So the payload capacity of your truck comes down. It is not competitive. So these are the factors which have to be taken into account when you make a choice whether you are going for hydrogen IC engine or a battery vehicle. That's why all this comparison I presented. It is basically for common man. You are all people who are going to make a choice tomorrow. The comparison only for that reason. Okay? आप कौन थे कुछ? Yes, somebody was asking. Same question. So answer is given already. तो अब माइक दे दो, इनको जरा सुनाई नहीं पड़ रहा.
So today when I go to the market to buy a car, it's quite overwhelming with options. Should I buy a petrol car, diesel car, or an electric vehicle? So it's pretty confusing for common people like us. So will there be any government policies or regulations to segregate the market into saying that two-wheelers is going to be EVs, cars are going to be petrol or ethanol blends, and trucks are going to be fuel cells or hydrogen fuels?
Government will not make such regulations. These regulations have to, there is no regulation in that. I will call it choice. The choice has to be made by the individual in its own utilization factor. That's why if more and more urban population starts using battery vehicles, automatically the IC engine driven vehicles will have a lower production rate. Today it is the other way. No? Even the two-wheelers, where a lot of battery systems are coming, the sale of the battery two-wheelers is still not higher than that of the IC engine two-wheelers. Am I correct? So penetration of any new technology takes time. The user makes a choice when it gets confidence with respect to range anxiety, safety and cost. These are the three parameters. In the case of battery vehicles, range anxiety still exists, safety still exists. Cost is comparable to the IC engine vehicles, only in the case of two-wheelers. But if come to four-wheelers, four-wheeler battery electric vehicles are costlier than the IC engine vehicles. So safety is common for whether four-wheeler or two-wheeler. So everybody will make a choice based upon these factors. That's why even after 5 to 7 years of major effort by the government of India in subsidizing the penetration of battery systems in the market, the success rate has not been very high. Yes, there is an increase in the utilization, but it is not as per our expectations. Okay? What happened? They have clapped already. Okay, go ahead.
But then what about the supply chain of this kind of thing? People might get into this, but is there any work being done?
How many people today are producing petrol at home? No, come on. Answer my question. How many people are producing biogas at home? How many villages are producing biogas for even cooking purpose? Although they have got wet biomass, agriculture waste, everything is there. See, these are all concepts that you can have a localized manufacturing for yourself, but it is not cost competitive. Even, I want to give you a picture. We were talking about garbage today while traveling. There are companies which are making garbage destroying system or garbage cleaning system or garbage system which can handle almost like a fridge. You put your house garbage and it gives you some ash which can be disposed of. I was talking to the company the company's name is Excel. The sale of that kind of a system is hardly anything. Whereas only the large size garbage cleaning system are purchased by the municipal corporations and things like that. So to say that this kind of a thing, a battery will be manufactured by individuals or biogas plant will be set up by individual for meeting his gas requirements, I think it is a far-fetched thing. It is not viable, it is not competitive. Okay, now clap again. ये निकालना भैया.
Sir, pen drive.
Thank you, sir, for your session. Now we'll have a short break for tea. So like we are running in short of time for the other sessions. So we'll be giving you for a 10 minutes break. So please assemble in the seminar hall sharp at 10:55. Please assemble at 10. No, sir. So please assemble at the hall exactly at 10:55. Thank you.
So we'll combine this also, one left. So the second one, Pradesh. First.
Yeah, no.
Volunteers, please assist the participants to get inside the hall. I request all the participants to be please seated in the venue. Volunteers, please assist the participants. Okay, we'll be starting the session. So before starting the session, I'll be giving a brief introduction about the speaker, Professor R.V. Ravi Krishna from IISc Bangalore. So Dr. Ravi Krishna is a distinguished faculty member at IISc Bangalore, where he has served since 1999. Professor Ravi Krishna's research spans combustion, atomization, and propulsion, with a strong emphasis on internal combustion engines and alternative fuels. His work has led over to 200 publications and impactful collaborations with leading industry partners, including Siemens, Pratt & Whitney, Tata Motors, Bosch, and HAL. He holds a degree from IIT Madras, the University of Alabama, and PhD from Purdue University. His contributions have earned him prestigious honors such as Professor Satish Dhawan Award, the INAE Young Engineer Award, and the Pratt & Whitney Chair Professorship at IISc. Beyond academia, Professor Ravi Krishna actively engages with national policy and standards, serving on committees for Bureau of Indian Standards and the Office of the Principal Scientific Advisor to the Government of India. He has mentored over 25 PhD scholars, many of whom now lead research at premier institutes. Please join me in welcoming Professor R.V. Ravi Krishna. Sir, please.
Thank you for the very kind introduction. So before I start, I just wanted to refer to what Dr. Saraswat said in his talk earlier. He was calling me his guru, but that is his humility. In fact, he's a real leading light for all of us. As many of you probably know, and some of you may not know, he has been leading the Combustion Institute for the last 20-25 years, and he has been a driving force for all of us and motivating us to get into new areas. Thank you. So, yeah, I hope you can all hear me now. So again, thanking Dr. Saraswat for motivating us to do this workshop and guiding us. Let me get into the topic. So I have about 20 minutes. So in this 20 minutes, I'll try to very quickly share a flavor of what we have been doing at IISc with respect to technologies for hydrogen utilization IC engines. I'm going to skip some of the initial slides. This has been covered extensively yesterday and today. And in fact, Dr. Saraswat has been, he gave a very long and very detailed talk about the hydrogen scenario in India, and it was very inspiring for many of us. So I'm going to skip some of these initial slides which talk about hydrogen as an IC engine fuel, and some of these challenges in IC engines were also, I think, spoken about yesterday by some of the, particularly from people from the industry. So I think, and some of the people from academia also. So pre-ignition being a problem, crankcase ventilation. But I want to highlight this point, which I think Dr. Saraswat also made, about lean combustion with higher compression ratios giving you the best efficiency. Now, this is something I'll talk a little bit more about, and of course the associated problems with that. So again, I think I'm going to skip some of this in the interest of time. Okay, so lean combustion, there are a lot of advantages of lean combustion. You can eliminate pre-ignition or knock. The problem that Dr. Saraswat mentioned about high NOx emissions can be mitigated to a large extent. Of course, from an engine point of view, you can do reduced throttling because it reduces pumping losses. And there are quite a few technologies that are available for getting to lean combustion. I'm going to focus on one such technology. And the second half of my talk, I'm going to talk about what we've been doing on the opposed piston engine. So this is sort of like the broad outline of the presentation that I'm going to be giving today. Now, pre-chamber combustion is something very interesting. Now, many of you who have been traditional IC engine students know that pre-chambers were used in old diesel engines, indirect injection diesel engines. But this pre-chamber concept is coming back in a big way for hydrogen combustion, and I'll tell you why. There are two broad kinds of pre-chambers, active and passive, it basically allows you to have stratified combustion in addition to homogeneous combustion. And in fact, pre-chamber combustion is being applied to not just hydrogen, but multiple fuels like gasoline, CNG, ethanol, and so on. And it allows you to have lean combustion, which again improves thermal efficiency, And lambda values as lean as 5 are achievable. When I say lambda of 5, that means the equivalence ratio is as low as somewhere around 0.2. So extremely lean or ultra lean. And that is also possible with pre-chamber kind of combustion. So here is what a deep dive into what is pre-chamber combustion. Essentially, you have a small chamber into which you either actively inject fuel and allow some combustion to happen, and those hot combustion gases then come out into the main chamber. So you can have a very lean mixture in the main chamber, and this rich combustion in this pre-chamber and the turbulent jets which are burning and entering this main chamber allow it to ignite. So essentially that's what it is. And this is some data from the literature that shows that this is very encouraging. And this is of course particularly on HCNG, where there's a mixture of hydrogen and CNG. Again, I'm going to skip some of this in the interest of time and directly go to the work that we have been doing at IISc. So at IISc, we do some fundamental work and we also do applied work. When I say fundamental work, we are doing work in a constant volume combustion chamber. So what happens here is you can do very fundamental controlled experiments. So you can have a fuel air mixture, any equivalence ratio. You can try any kind of ignition system. You can try a conventional spark plug. We have been doing some plasma ignition, so we can try all of that. And the nice thing is, this chamber has multiple windows, so you can actually visualize the flame as it is moving. So you can make measurements of flame speed. Although it's an idealized situation because it's a nice laminar environment. It's not a real engine where there's a lot of turbulence, but it still allows you to test a lot of concepts and understand fundamentals. So we did a lot of interesting work in this chamber. So here is a picture of the chamber. Of course, you have windows on either side. This can be replaced by a window. And in fact, this is a picture of a nice, so this is your spark plug. The mixture gets ignited and you can see this nice flame front which travels all the way and consumes all the gas. And here we have been trying a lot of research on ignition systems. The time is very limited. I'm only going to give you a flavor, as I said. So we have been looking at thermal plasma ignition systems and also non-thermal plasma, which is a very interesting thing. I will not be talking about non-thermal plasma in this talk because it's a separate, it will require a lot more time. But these kind of nanosecond pulse discharges have also given us some very encouraging results. So I just wanted to show you that we have been doing also this kind of work. So this is sort of a schematic of the test setup. Again, you have the constant volume chamber, and of course you have some backlighting, and then you have a high-speed camera. So essentially what you're doing is you're looking at a shadow of the sort of flame that is traveling across. So it is like basically high-speed shadowgraphy, as we call it. Okay, so of course this is just a picture of the setup. So you can see the constant volume chamber here, and of course this is the high-speed camera, and you have all the optics here for the backlighting. So I'm going to show you some sample results in a minute. So here you can see, I hope you can all see the video. So you can see how the flame is traveling. This is a spark plug, conventional spark plug. This is a pure methane flame. This is 18% hydrogen. I'm sorry, let me go back. Just go back. And the middle is actually HCNG, which is 18% hydrogen, 82% methane. This is 50% blend of hydrogen. You can clearly see that the presence of hydrogen dramatically changes combustion. It accelerates combustion. The flame is now traveling extremely rapidly. So, so this is inside this constant volume chamber. And so what I'm trying to say is that these kind of experiments give us a lot of insight into how the flame is actually going to behave inside the combustion chamber. Of course, there's a disclaimer. This is a nice laminar flame, whereas in the real IC engine, you have a highly turbulent mixture which tends to accelerate. But this still gives you a very good idea of what to expect when you bring in hydrogen as an IC engine fuel. Now, so I was talking about pre-chambers, right? So a passive pre-chamber is when the mixture inside the chamber sort of goes back during compression, the same mixture goes back, ignites, and then comes out as a burning jet. This is an active chamber where you're actually injecting some fuel. So you inject the fuel into the pre-chamber. So you have a rich mixture which burns and then the jets come out. I'll show you a video of this very shortly. So basically we have been looking at this pre-chamber technology very actively, both from a fundamental constant volume chamber point of view and also in the IC engine. So, so again, I'll skip the details, but we have started to look at hydrogen methane blends. But we believe that pre-chamber is an excellent method to implement ultra lean combustion of hydrogen. Of course, there will be issues like NOx. I'll talk about that a little later. So here is probably, I have to just run this video. I hope it runs. So yeah, this is a passive pre-chamber. So we have a passive pre-chamber, and you can actually see, this is the pre-chamber. This is a conventional spark plug, okay? So you see the flame moving around. Of course, this is a methane air. There's no hydrogen here, it's methane air. But I'll just show you what happens when you have a pre-chamber. So that will give you an idea of what I'm talking about. So when you have a pre-chamber, the combustion is happening inside this pre-chamber, and now you can see these turbulent jets come out. And you can just qualitatively, you can see that the propagation is accelerated, right? It's consuming the fuel air mixture much more rapidly. So you can clearly see an evidence of how a pre-chamber accelerates combustion and so on. And this of course with methane, but with hydrogen, of course, you expect even maybe a very different. We have not yet done experiments. In fact, some of the experiments with hydrogen are ongoing as we speak. But you can get a lot of data from this. So there's some data here. We have looked at different kinds of spark plugs. We are looking at passive pre-chambers. Again, just to give you a flavor of what we are doing. So since the time is available is less, I'm just going to move ahead. And so this is the actual data. See, in the constant volume chamber, you see that with the conventional combustion, this is the rate of pressure rise. This is pressure versus time. You see that with the pre-chamber, you definitely see a much more steeper rise in pressure. And that is what you want, right? You want faster combustion that has a lot of benefits in terms of better engine performance, better efficiency. And you can see this in terms of heat release rate. The dotted line is the conventional heat release rate, and the solid line is the pre-chamber. You can see that with the pre-chamber, the heat release is also much more accelerated. You can see that very clearly from both the pressure and the heat release. So, so we have created a small engine test facility at IISc. Of course, this took a lot of effort and funds and resources, but I'll just show you a glimpse of, so this is a completely remotely operated test cell. So we have the engine and the dynamometer inside, and the operators actually sit in a different building. So in terms of safety, we have ensured that this is this is implemented. Inside we have a lot of other features. So for example, we have all hydrogen rated pipelines. In fact, Dr. Saraswat was talking about some of the standards of hydrogen. So we have implemented all of those. There's automatic shutoff. So if it detects hydrogen leakage, there's an automatic shutoff of all the valves from the hydrogen bay. There is active fire suppression. So there's a sensor. If it detects hydrogen, it immediately injects a gas called HFC, one of the HFC gases. So it suppresses fire. So this facility is now rated for hydrogen, 100% hydrogen engine tests. So we have an office of laboratory safety on campus. Unless they come and certify, we are not allowed to do experiments. So this office has actually certified this facility for hydrogen usage for small engines. I have about 7 or 8 minutes left. So I'm going to quickly talk about the opposed piston engine, about which Dr. Saraswat also made a mention. So I borrowed a slide from this startup called Ecatis Power. This is a very successful startup in the US. They've been around for 20 years. They've built this opposed piston engine. So you can see that these two pistons are moving against each other. So it's essentially like a two-stroke. It's a two-stroke concept. You can see the ports where the fresh gases come and the exhaust goes out, and the two pistons are moving against each other. So there's no question of a cylinder head. There are no exhaust intake valves. So the mechanical complexity comes down, and they have actually built a diesel engine with this technology. In this case, you can see it's a 3-cylinder engine. And one of the diesel engines that Achates has developed, and it has been actually measured and it is now powering a truck in the US, has delivered 50% brake thermal efficiency. Now, all of you know that 50% is unimaginably high for an IC engine. In fact, if you remember the plot that Dr. Saraswat showed about how fuel cell efficiencies come down with power and IC engines sort of increases, and both of them are meeting somewhere. I think you remember that plot he showed about the efficiency of a fuel cell versus an IC engine, how they are meeting. So this technology promises to bridge that gap. So if we can, of course, this is 50% is with diesel. So there's a lot of research going on around the world on hydrogen opposed piston engines. And if you really get 50% with hydrogen, then that's jackpot, because then it can easily beat a fuel cell. So I'm going to skip again some slides. These are some advantages. So yeah, so there's a case for hydrogen opposed piston engine. And interestingly, it's called HOPE, H-O-P, hydrogen opposed piston engine. So there is a lot of hope for IC engine community that if we can actually hit that high efficiency, then we can beat fuel cells. So again, the case for hydrogen for hydrogen opposed piston engine is that you can get very little NOx. I'll tell you why in a few minutes. And then of course there's a promise of very high efficiency. So I'll move fast. Yeah, this is the plot that I again borrowed from Achates Power. This is their load speed curve for the diesel engine, and these numbers are not visible to you, but they have actually hit 50%, and this whole red region is 47 and high. So many of you know that in an IC engine, the load speed curve, you only have one sweet spot where the efficiencies are high, right? Fuel consumption is low. Look at this plot. It's not one sweet spot. There's a whole red region where the efficiencies are 47% high. So that's the beauty of this technology. You get a very large range of high efficiency conditions on the load speed curve. So regarding the design development of this engine at IISc, conceptually it's a simple 2-stroke engine with uniflow scavenging. That means a fresh charge comes in and goes out from the other side. And we did a lot of CFD work to optimize the scavenging port design. And again, in the interest of time, I'm going to skip all of this. We've optimized the port angles, the port areas. This may not be of much interest. I'll just show you a sample. So we did a lot of optimization and came up with a lot of different angles. Essentially, everything was based on very elaborate CFD simulations. We used the DOE approach, so there were literally probably more than 50 to 60 simulations that were done. So this one just shows you an idea. I mean, it's a simulation, video of a simulation. So you can see that this is in-cylinder scavenging happening. So you can see that once it opens the ports, the gas comes in, the fresh charge comes in and pushes out the exhaust. And then, of course, we look at what is remaining inside and we ensure that you have a flammable mixture. Now, again, if you remember from Dr. Saraswat's talk, he talked about NOx being a big challenge, right? Now, in 2-stroke engines, the beauty is you can manipulate your scavenging process in such a way that you ensure that there is some leftover gas from the previous cycle. So it's like internal EGR. I think all of you know what is EGR, exhaust gas recirculation. In a 4-stroke engine, you have to purposely bring exhaust gas back into the cylinder. Here, in a 2-stroke, you don't have to do anything. You just manipulate your port in such a way that some of the gas stays inside from the previous cycle. So it's automatically doing EGR for you, which means it is lowering temperatures, which means it is lowering NOx. So that is the beauty of the 2-stroke concept for hydrogen engines. And so, of course, we have built a lot of not just CFD models, but also engine models. This is a software called GT Power, which enables you to build an entire engine model. Again, so we have done all of that. And this kind of model helps us to, for example, optimize stroke to bore ratio. So we have to figure out what should be our stroke to bore ratio. This is very important for many of the things. So we have done all those simulations and with the model, and we have arrived at what should be the design. And conceptual design is basically, so what we have done is to speed up our development. We have actually borrowed, we have taken commercially available 2-wheeler engines and we have taken some parts from there, including pistons and other sort of components. And we are trying to build a prototype from this, some of the parts that are commercially available. Of course, some of the work is still ongoing. Some of the combustion system processes optimization is going on. And Again, we are planning to use low pressure hydrogen fuel injectors for this. Again, these are port fuel injectors. Of course, they are not shown in this diagram, but we are planning to use, probably you can see it right here. The fuel injector is shown here. So we use low pressure injectors to inject fuel into the hydrogen into the cylinder. So here are some CAD models of our prototypes. This is actually the optimized engine cylinder model, and of course these are all, this is the final assembly because you need to have all the manifolds, intake and exhaust manifolds. So this is sort of now ready. We haven't fired it yet, so in the next few months we'll be actually firing it, and then hopefully we will be able to get some performance data. So, but we are still there, and these are, in fact, we have printed some parts of the 3D printed engine parts can be seen here. We've used SS316 and aluminum. So the cylinder and exhaust manifolds are made of SS. Intake and manifold, intake port, sorry, and intake manifold are made of aluminum. So you can see some of the parts here. So these are not yet fired. This will all happen in the next few months, and we hopefully will start to generate some data. So I think I'm exactly in time, 11:20. So I will stop here. Thank you very much. Maybe I don't know if there is time for questions, but if there is, we can take one. Thank you.
Coming to listen you, I told him that he is speaking, so he was in the meeting.
So I can present to him separately. I'll tell him I'll come and meet him.
Okay.
Yeah.
We'll take one notch in the reference.
Yeah.
What is this GT power model? What is this?
So GT Power is basically an engine simulation software. It is basically to where you can model the entire engine. So the cylinder is basically 0D. No, it is designed particularly for IC engines. Yeah, not gas turbines. So it's the cylinder is modeled as 0D and the manifolds are 1D intake. So it's a combination of 0D, 1D. So that's why it's a very, you can run it very quickly. The simulation can be run very quickly. Yeah. Okay. Yeah. Thank you. Thank you all.
I now invite Dr. Vivek V, Professor and Deputy Director, Alliance School of Advanced Computing, to present a token of our appreciation to Ravi Krishna, sir. It is my pleasure to introduce our next speaker, Dr. Irfan Mullah, Assistant Professor at the Indian Institute of Science, Bangalore. Dr. Mullah's research lies at the intersection of combustion diagnostics, emission control, and advanced laser-based measurement techniques. His work focuses on understanding the formation of soot, nitric oxide, and carbon monoxide in both academic laminar burners and practical gas turbine combustors. With a strong foundation in spectroscopic modeling, his group develops high-fidelity diagnostic tools to quantify emissions and improve combustion efficiency. Dr. Mullah earned his PhD in experimental combustion from IIT Madras and went on to pursue postdoctoral research in the UK and France. He was awarded the prestigious Marie Curie Fellowship at Imperial College London and served as a visiting researcher at University College London. His international experience includes advanced emission studies at CNRS in Rhône, France. His contributions span turbulent mixing, flame stabilization, ignition dynamics, and emission modeling, making him a key voice in sustainable combustion research. Please join me in welcoming Dr. Irfan Mullah to share his insights with us today.
We have 3 papers now. First paper is with Mullah, it will go. Please go ahead.
continues. Am I audible to you? Yeah. Yes. Okay. Right. All right. So I'm Irfan Mullah. So I'm presenting a work of my student Aditya Chaudhary, who is doing.
Mullah, you have 15 minutes of presentation.
Sure. I'll do that one. So the topic of my today's presentation is effect of hydrogen enrichment on soot formation. This is more of a fundamental work than applied that you will see now. So I'll briefly introduce in combustion what do you have. There are three domains: measurements and chemical kinetics, and then you have reacting CFD. So what reacting CFD is required is reduce chemical kinetics model. Your number of equation and complexity increases if you give very large set of reactions. So we do measurement here, and then those that data goes into tuning the chemical kinetics, and that will eventually go to reacting CFD. That's the whole idea. And our domain of work is NOCO and soot formation. All right. So that's basically when I say measurement, we use laser-based techniques, and you have laser that creates a sheet, and then that excites certain molecule, and you have camera on other side that captures the signal. And by tuning excitation and detection wavelength, you can target different species such as NOCO, NOH concentration. You can obtain the concentration of that. Okay. All right, I think. Okay, this is better. There's some lag, please. Okay, this is good. So this is example. What you see is laminar flame, and in that example, you see soot precursor pH, soot concentration, and OH radical. That all this information and temperature is obtained by using laser-based techniques. So you don't put any probe. I have shown the setup previously. Use that kind of setup, change excitation and detection wavelength, and by using that, you can get this kind of high resolution information without putting any physical probe. And here we are trying to see what's the impact of hydrogen on soot. We have a set of another laminar burners, and on the right corner over here, what you see is in this kind of burner, we have measured nitric oxide. That also comes from laser-based technique. And on the right, there are two sets of marker. One set of marker is experimental measurement. Other set of markers is coming from chemical kinetics simulation. So, and this axis over here is equivalence ratio. So we also look at not only laminar flames, also turbulent flame. This is a rich quench-lean gas turbine combustor. So the one sector of the combustor, and the typical flame will look like that. It's a very sooty flame with ethylene fuel. And if you, there is other holes over here, that is for second stage of combustion. So you do rich combustion here and lean combustion over there. And your transition, this you do for low NOx, but the rich case will generate soot. And when you put on the dilution air, that soot gets oxidized. So these are the pictures over here. On left side, you see a soot concentration information, and then you have numbers in ppb. And over here, we also looked at cold flow air fuel mixing. So this axis is representing equivalence ratio or fuel concentration. So you have rich mixture here, and then injection of air, pure air, and then mixing occurs, and you have lean mixture. That's a transition. On the right, you see a velocity field that we obtain using a technique called particle image velocimetry. So that's an example of these capabilities over here. Now, why soot emissions are not good is, I think this previous talks were speaking of particulate emission and NOx emission. Not only for IC engines, for aircraft engines, if you have soot emissions at particular altitude, they will act as a crystallization site, and you will have formation of contrails that you can see in the sky. And this is basically condensation sites and formation of crystals, liquid and then ice crystals due to colder ambience. And this is mainly H2O that traps the heat. So this leads to global warming. So that's why this kind of emissions are controlled. If you want to sell your engine, it needs to be under certain emission control. So That is a jet engine, and the fuel you use is C12 to C16. That's a carbon chain. Typically, it will have alkanes and to some extent aromatics. Now, this is very complicated fuel to handle, and academically, we are somewhere over here. We know the chemistry of the C2H4 ethylene very well, and maybe these are getting developed. We are a bit far from understanding chemistry for that part. So our approach is to start with very simple fuel, generate flames, so provide the database, and hope is eventually we'll bridge that gap as well. Now, that's what I was mentioning. So in chemical kinetics aspect, hydrogen oxygen chemistry is very easy because set of reactions are low. Next level of reaction will be CO chemistry. Again, set of reactions are low, and then you have methane chemistry, and the carbon number progressively increases. So chemistry for higher hydrocarbon will be based on the simple chemistry of your H2O2 and CO and so on. So build step by step, and our data will go into somewhere in these folders over here. So that's a laminar flame, burner stabilized over here. That's one-dimensional flame, easier to simulate. And you see a soot forming. There's a flame somewhere here, and the top plate to stabilize the flame. And you see soot forming over there. And this luminosity you see just like your electric bulb incandescence coming from the soot. Now along this side, what's happening over here is you have pyrolysis of your incoming fuel rich, you have formation of polycyclic aromatic rings, aromatics, and eventually that aromatic size grows and you have inception of first soot particle, and the particle also grows along this direction, and the growth can be described by C by H ratio of that particle. So essentially incipient particle will have less carbon and more hydrogen, and eventually carbon will start to dominate and it can go to pure carbon. So that's the whole idea over here, and we do 1D flames and we do measurements. Now that's the burner details. Burner looks like that. Okay, in the measurement technique, what we do is we put a laser sheet of 1064 nanometer infrared wavelength, and since this is a black particle, it will absorb that radiation and it will get heated up beyond the flame temperature. So it will have its own incandescence beyond this natural luminosity. So you can get a signal out of that. And that signal is proportional to soot volume fraction. That's the entire principle of the measurement. So this curve is showing that your incandescence signal as a function of laser energy, you start to have suddenly a signal coming from soot radiation in soot incandescence, and then you suddenly have plateau. And this plateau occurs because the soot particles sublimates due to absorption of too much of energy as a function of energy over here. And that's a typical trend, and people do experiments around that point, so there is no sensitivity to your laser energy variation. Here is a picture, and here is the measurement capability. You see a soot concentration obtained using again non-intrusive method in ppb. So you need to calibrate that signal. So the way you calibrate is basically you have fog and you don't see when there's a fog, when it rains and all those things, because light cannot gets absorbed or scattered. The same principle applies here. If you pass through laser beam through the soot, you will have less intensity due to absorption of this light by particles or scattering by these particles. And by looking at certain constant, you can get to soot concentration. So that's the way we calibrate our signal. Now the problem comes, you have this absorption occurring, and this is the optical technique. Now problem comes that which property do you use? What kind of optical property do you use? And this plot is showing it's the same measurement. Different people have measured around the world, mainly Germany and USA. And you have scatter, right? These are all these lines of soot volume fraction or soot concentration as a function of height. The last scatter over there. And this comes from the variable property of absorption property that changes from 0.3, 0.2, and so on. So if you normalize that, you have reasonable collapse, but still some data lies away. So there is a lot of measurement uncertainty, and our group is specializing in how to get this data very accurately so that we can transfer with some confidence to people who are modeling chemical reactions, so that mechanism is right, and eventually you can use that in reacting safety in practical application. So we come up with approach to get the optical property variation as a function of height. So what happens over here is at lower height, your soot is not going to absorb that much of laser energy because it has, let's say, equal contribution of C and H, and eventually you have more C, meaning that more absorption as you go downstream. as height increases or composition changes along the height, you will have sublimation occurring at lower fluence. So that's the whole idea. By using this laser energy versus LII signal, you can get to optical properties of soot. So that's our approach. By doing that, we come up with this curve over here. So we say that optical property absorption of soot changes in this manner, that bottom curve. If you don't, and then top curve is showing the temperature variation along the height of that particular burner. So this curve is signifying the importance of doing that correction. The first line over here is uncorrected, dotted line is corrected. If you don't correct, you have slight error, and the bias is very high. For example, at particular height, bias could be at let's say 6 mm above the burner, bias could be about 100%. So this kind of accurate result you can get. Now this picture is showing as a function of fuel, you start from methane and then propane in this case, butane and ethylene, how the total soot loading changes as a function of fuel. So this is expected curve, but we get quantitative number out of that. Now we can give this to chemical kinetics people who are doing modeling. They have very accurate data for basic fuel. So basic chemistry is not incorrect, and they can build upon chemistry for practical fuels, C12 onwards. And that's the intention of doing this experiment. Now we ourselves tested the simulation, so you can do 1D simulation. This is chemistry simulation, a bit involved. For that we use a certain mechanism from developed by Italian groups, and then this line over here shows the measurement, and the magenta line is showing simulation. So what you're saying in simulation, soot onset occurs way ahead. So from this we can tell that there is need to revise the soot inception rates, because it doesn't match experiments, and in experiments you see soot start to have onset somewhere there. So there's something, some additional work need to be done on reaction modeling side. Now that was with 0% hydrogen. If you add hydrogen, here's the picture. So what we do over here is, we know that inception rate is, there is some offset into that. So we move that inception line, simulation line, and at least see if growth rate is matched. Growth rate comes out reasonably, but it's still on lower side. So even if you do this shift accounting, so both inception rate and growth rate chemistry need to have revision. And in the case of hydrogen, results don't match at all. The growth rate is just too high for simulation. So this is significance of doing a simple 1D flames measurement and seeing what's the impact of hydrogen. It just doesn't work because the chemistry has been tuned to methane or ethylene air kind of configuration without any addition of hydrogen. So we tried this with different fuels. In this case, it's ethylene plus oxygen, increased content of oxygen. Does it match with increased content of hydrogen? Sometimes it does match, sometimes it's not. So it's not that consistent. Fuel here is ethylene and O2. Now next case you are seeing, now we started to go from C1, methane to butane. So you see results from methane and ethane over here. So methane growth rate reasonably predicted. All those curves are shifted, by the way. You see a shift here, 4 milliseconds. So inception rate never matches, and those numbers chemical kinetics people can use and tune their kinetics. So results are there.
You have 2 to 3 minutes.
Yeah, I'll go to conclusion. So we have results, a lot of results for other flames like propane, and we always give the numbers for inception rate and growth rates. And this data eventually we will give it to international shooting flame database. And here are the results for butane. Now we can go to directly a conclusion slide. Yeah, so conclusion of this work is there is something called International Shooting Flame Community. So that collects databases from all over the world, from Germany, Australia, KAUST in Saudi Arabia, places like that. And they will use this data, and there is simulation community is also there. All this is for laminar academic flames. But once you tune the model, you can take it to any practical configuration. After you reduce that chemistry to have a suitable computational arrangement to run on your available resources, and then eventually you can transition to gas turbine combustion and soot prediction over there. That's the whole idea of doing this work. And we see main idea that with addition of hydrogen, you need to change the kinetics, and if you use existing chemical kinetics, you're not going to get any better prediction in IC engines or gas turbines. So if this is refined, those prediction will improve. Thank you.
Thank you, Professor, for the nice presentation.
Yeah.
We can take 1 or 2 quick questions.
Yeah, please. Can you use mouse?
So what was the reason for selecting ethylene? Is it going to be a future fuel, or what is thinking behind it?
Reason is it has been academic fuel and it has more shooting tendency. So measurement will be accurate. There is no other reason apart from that. So ethylene is not practical fuel. Practical fuel, if you go to gasoline or diesel or jet fuel, all are C12 based. So it's an academic fuel which suits more, so your measurement accuracy improves. And it's traditionally been used over the decades. So yeah. No?
Thank you, Professor.
Thank you. Yeah.
Thank you, sir, for that talk. May I now request Dr. G. Ramanamurthy, Professor and Program Director, PhD, Alliance School of Applied Engineering, to kindly come forward and hand over the gift to sir. It is my distinct pleasure to introduce our next speaker, Professor Aditya Konduri, someone whose work sits at the cutting edge of computational science and engineering. Dr. Konduri Aditya is an assistant professor in the Department of Computational and Data Sciences at the prestigious Indian Institute of Science, Bengaluru. He leads the FLAME laboratory, where his research spans a fascinating intersection of computational fluid dynamics, turbulent combustion and propulsion, high-performance computing, and scientific machine learning. Dr. Aditya earned his PhD in aerospace engineering from Texas A&M University, where his groundbreaking dissertation on asynchronous algorithms for partial differential equations earned the department's Outstanding Dissertation Award. He later continued his research as a postdoctoral scholar at Sandia National Laboratories in the United States. His contributions have been recognized with several accolades, including the Arkot Ramachandran Young Investigator Award in 2022, the ASME Turbo Expo Best Paper Award in 2024, and most recently, the Dr. APJ Abdul Kalam HPC Award in 2025. Please join me in welcoming a visionary researcher and a rising leader in computational sciences, Dr. Konduri Aditya.
Thank you very much for a very generous introduction. I'm not sure if I'm... Okay, anyways. So let me...
You have 15 minutes.
Yes. Let me do this very quickly. Thank you very much for giving this opportunity. Today I want to talk about how we can bring all the buzz around machine learning and AI into combustion systems, right? First word of caution is that machine learning and AI cannot replace anything that we are doing. What it can only do is accelerate the kind of things that we are doing, maybe by a significant amount of time scale that we want to incorporate into engine R&D and operations as well. So just to give you a quick overview, right? So now we are looking at energy transition. We want to go towards net zero energy, and the possible candidate fuels are hydrogen, ammonia, biofuels, and so on, where you in total want to maintain a net zero. I don't want to go into the more details, but what lies ahead are the challenges in realizing those systems. For example, we want to look at low NOx systems with high combustion efficiency that works across different fuels. So that means you are looking at fuel flexible engines, and you want to integrate these combustion systems along with carbon capture and hybrid systems to get the entire energy economy, right? And finally, as you move towards hydrogen, operational safety is paramount. So can machine learning really help in this aspect? To understand this, first we have to understand combustion, where combustion is a multi-physics, multi-scale, phenomena with complex chemistry, and things are highly nonlinear in nature. That means the linear predictions will not work. You have to have really high fidelity models to be able to understand these complex nonlinear physics at conditions of practical relevance. Here on the top, I show you a CFD simulation, and if you actually look at where the chemistry is happening, it's happening at molecular scale, where atoms collide and form water and other radicals, right? So what are the major challenges in terms of combustion research? The computing cost is really high when you go to combustion simulations when compared to other CFD, and it is very difficult to do real-time control and diagnostics, and also there is large uncertainties associated with the combustion chemistry because it has large mechanisms, as Irfan illustrated in the previous talk. So if you take a typical design cycle of a gas turbine engine, maybe from R&D to realization of the first engine, it might take about 7 to 10 years. I'm being very generous here, but that's how the time scale is. So now the question is, can machine learning be used in accelerating this cycle, right? So that is a question that I want to answer. And in this talk, I will not be going into any of the detailed concepts. I want to give you an overview of several examples on how machine learning is being used in combustion. And if you are interested, you can talk to me after this, or we can chat by email. So a quick primer on machine learning. So the entire machine learning framework is divided into 3 areas. The first is supervised learning, where you have data where someone sits and labels the data between inputs and outputs. And this further divides into classification and regression algorithms. Classification is mainly whether things are working fine or not, yes or no kind of answers. And where regression is where I have these conditions, give me what is the best parameter. So you fit some regression line and you get the outputs. The second one is where I have data, but I don't have any labeled outputs, input-output pairs. Here where we want to use clustering algorithms and look at unsupervised techniques, right? And finally, if you want to do any control process, there is something called reinforcement learning, where it uses a reward mechanism to optimize its predictions and control algorithm. Finally, all these things are further divided into 2 areas. One is the statistical learning, which is the traditional statistical methods towards adapted to large data. And then you have deep learning, which starts from ANNs all the way to ChatGPT that we are all familiar with. So the recent advances in this include foundational models, which is what people are looking at. And finally, you have generative models. That means what I learn from data is the underlying distribution. Now I have learned the distribution, now I can sample data at any condition or a combination of conditions, and I will be able to predict things. So these are what generative models are all about. And finally, the reinforcement learning and the new architectures. So usually, if you are looking at Netflix predictions or Amazon predictions on what you are going to buy next, it's okay, right, if it goes wrong. But if you are in healthcare or in scientific computing, right, you cannot go wrong. Okay, so and things are highly nonlinear in nature. You have to have the physics consistency. You cannot have biases, right? And you have to have data efficiency, because scientific data is sparse, while data that we use for Netflix predictions or cat or dog predictions is quite large in nature, right? The entire internet is available for such data. So the key approaches where scientific machine learning branches out from traditional machine learning is physics-informed neural networks. You have what are called the neural operators, and you can combine all of these into hybrid models. And further, to understand how these models perform when there is some uncertainty in the parameters, right? You also can do uncertainty quantification based on one of the methods is the Bayesian inference method. So now towards combustion research, what are the ML capabilities, right? If I want to really talk broadly, it can be used for pattern recognition and knowledge discovery. You can create reduced order models. My CFD simulations are going to take 10 days time or 1 day time or 5 hours time. Can my reduced order models that I obtain from the training on the CFD data can predict these things in a couple of minutes. So that those are the kind of systems that we are looking at. And then parameter estimation. So for example, I have a lot of data on the plane speed and I want to estimate the parameter of one of the rate constants. So can I do that the parameter estimation? And finally, the control and optimization, which I'll show one example on. And in terms of combustion applications, so these can be used in 4 different ways broadly. First is chemical kinetics and fuel design. For example, earlier many speakers talked about blending hydrogen with methane or blending hydrogen with something else. right? What is the right blending proportion, right? So those kind of things can be done in this context, right? And then combustion modeling and experimental diagnostics and so on. So at a kinetic scale, right, in my lab we are looking at molecular dynamics, where we are developing a new paradigm on improving the accuracy of MD to predict the entire chemical kinetics in a single go, right? And in this process, machine learning is being used to develop ab initio MD scale accuracy with reactive molecular dynamics or force field based dynamics, which is much more less expensive. In this context, there has been a paper in Nature Communications where people are able to show the accuracy of machine learning potentials with a great amount of fidelity. And the cost of these things is realizable for even complex hydrocarbons. The next one is fuel design. So these are work from KAUST in Saudi Arabia. What they have done is they have taken a database of measurements that they have done through experiments, and in this process they have developed a generative model that trains on this data. So now it has two things, right? It has the kind of chemical inputs that you are giving in, which is, for example, the composition of your fuel. Then it has a mixing operator which does what is the mixing fraction between the different components, and then finally it does the prediction based on the mixing operator of some of the properties, and finally goes towards your engine scale predictors, right? If I want to, for example, optimize for soot index, right? What is the right mixing operator and what is the right mixing fraction, right? So these are the kind of optimizations that are able to be envisioned through machine learning processes. Another example, this is done in my own lab. We are looking at Ansaldo Energia's reheat burner. So this is a two-stage combustion system, right, where the first stage is aerodynamically stabilized like any other burner, right? The second stage has products from the first stage. So now the reactants are at vitiated conditions, right? So now this flame can be stabilized in a spontaneous ignition mode. So the overall characteristics of this combustor are governed by the second stage predominantly. And when they were looking at burning hydrogen in this, they were seeing a lot of issues. So what we went ahead and did is we did a scaled DNS, direct numerical simulation, with fully detailed kinetics of this burner that you see on the right hand side. So just to give you what this simulation costs, right? It's fully direct numerical simulation. It solves for the 5 conservation equations plus the 9 chemical species for hydrogen mechanism. We use about 2 billion grid points and 1 million time steps. The CPU cost is about 20 million CPUs. So these are really expensive simulation, right? But when I do such a simulation, what do we get out of it? Am I doing something different? And is it going to impact my engine design? That is a question that we want to answer. So the initial engine or the concept was envisioned to stabilize the flame mainly in the spontaneous ignition mode, which is the green color shown here. But what you actually find is the reactants that are in the near wall region are cooled because of the wall cooling, and their ignition delay time increases significantly. And what happens is now the flame here is stabilized by flame propagation mode. And we were able to quantify the amount of fuel consumed in each of these modes. Okay. In addition to this, because hydrogen was used, we were able to understand the mechanism for a flame induced instability. What happens is, because the flame auto ignites, it releases a pressure wave in both the directions. So the pressure wave that goes to the left does PDV work on the reactants and it reduces the ignition delay time. Now this ignition kernel spontaneously ignites in what is called this mixing duct, which is not desired, and this eventually results in a flashback, right, which is not desired. So now the question is, we understood the mechanism based on the flow physics, and the next question is, can we really use machine learning to control this? Before I mention about it, this is the overall schematic of how a typical solver works for combustion modeling. You have governing equations, you have a solver, you have initial boundary conditions, you have a subgrid model, you generate data, you post-process, and you understand the fundamental insights. So now how can machine learning come into this picture, right? In terms of governing equations, using machine learning, instead of solving for all the 9 species, I can now solve for 2 or 3 species which are in the reduced dimensional manifold. And I'll show you an example for this. Next is in terms of initial conditions, right? We can use what is called a super resolution algorithm where we can use low fidelity simulations and generate high quality initial conditions for my high fidelity simulations. And then in terms of boundary conditions, for example, I want to generate realistic turbulent inflow, right? The generative models are now capable of generating turbulent inflows that maintains both spatial and temporal correlation lengths and time scales. And finally, in terms of LES, you can use parameter closing using machine learning, where different flow regimes that demand different parameters are automatically adjusted using a machine learning model. And finally, once you have the data, right, what can we do? We can do analytics using machine learning to detect extreme events, right? Any event that you are not anticipating if it occurs, can we capture its inception? Can we capture its precursors? And finally, create reduced order models for engineering design. So this is the whole big picture. And these are the set of equations that we solve. Typically, these are about 100 equations. When you take a complex fuel, it has about 20 to 500 reactions in a DNS kind of a setting. So now just to understand how low dimensional manifolds work, let's say these are two variables x1 and x2. These are the data points that come out of my simulation, right? Now what we can do is we can perform what is called principal component analysis, and we get these vectors which are a1 and a2. Now I project the entire data into one of the vectors where you get some projection errors. Now I am going to solve only for one equation. Just to understand this further, if a reaction goes as a plus b gives c plus d, where I have to solve for 4 equations. Now if I put this into a low dimensional manifold with some reasonable accuracy, I can now solve only for 2 variables, reactants, these products. So these are the kind of data driven reduction techniques that we are looking at. So the principal component analysis is widely established, and what we have developed in our lab recently is co-kurtosis based principal component analysis. The reason for this is flames occur in a very thin zone. They are not well represented by the entire combustor length or the entire data set. So we use what is called this technique, which I will show you in some time. So this is the entire dimensionality reduction technique, where the entire process can be envisioned as a autoencoder process, right? You have your initial condition, you project the data into the low dimensional space. Now you do all your CFD computations in this low dimensional space, and when you have that solution at all the time steps, you project the data onto high dimensional space. In this process, we use autoencoders, neural ODEs, and artificial neural networks for the data reconstruction. And finally, what do we get out of it? So some of the people, our collaborators at KAUST have done this. So for example, in this case, a DNS simulation with 11.5 million grid points, similar accuracy results were obtained with 3.4 million grid points and with a time step much larger, which means my speed up of about 70x was achieved in this simulation. So it's 70 times faster when you are looking at high fidelity simulations. Similar things can also be replicated for other low fidelity simulations. Okay. Finally, the super resolution technique is what typically our phones do. We take our images in a very low resolution, poor lighting and so on. The machine learning algorithm working on our operating system will enhance the quality, that is what we try to do for flow field simulations and flames as well here. So recently one of my students has done a really first DNS of a hydrogen IC engine, right, where we look at the propagation of the spark and the flame front. He was able to use this data set and generate the super resolution algorithm, and it works really well. This got published in ECM, and now we are looking for a paper towards combustion and flame. Finally, here in this example, so earlier everything was related to simulations. Now we want to look at experiments. How we can help experimentalists get more insights.
2 to 3 minutes.
Yes, yes. So in this work, we have collaborated with Professor Ravi Krishna here. This is the trapped vertex combustor rig. What they can measure here is only OH star chemiluminescence. What we have done is we have done LES similar to these conditions, trained a machine learning model. Now, if we put a OH chemiluminescence image, we are able to get the velocity vectors out of it by training this model. And with this, we are able to get the vortex configuration that helps you understand how the flame is stabilized. So we are able to augment experimental data analysis with machine learning model. A quick this thing on our method. So this is the standard PCA, this is normal data. This is data with some abnormality where you have these anomaly points presented here. PCA is very insensitive to these distributions. However, when we do what is called co-kurtosis PCA that we developed, the first principal vector quickly orients itself to the extreme event. If I change this randomly, right, it always orients to the extreme event. So this is a kind of technique that we have developed which helps us understand the precursors for extreme event and helps us quickly detect this. We implemented this for the flashback case. So now you will see the flashback here, right? We implemented this in the flashback case, first in the LES data where you have the entire state. Finally, this obviously cannot be used in actual operations. So we also developed one more case where we have 5 sensor, pressure sensor data. So now we are using only 5 sensor data in a time streaming manner, and we did the analysis. And I will not go into the details, but what I want to show is this is the data for normal operation. This is the inception of extreme event. This is the extreme event. And in all of these cases, we are able to predict that a priori. And once we predict that, we inject water and prevent the flashback. Right? So this entire thing was data driven using machine learning algorithm. So with this, I want to conclude my talk. The overall message that I want to give is machine learning can be used to accelerate and complement some of the traditional analysis that is being done in combustion science and engineering operations. Broadly, we can use for feature extraction and all of these things. And finally, I want to acknowledge my students and collaborators in getting this volume of work done and all the funding from different sources. Thank you.
Thank you, Professor Aditya. We can take 1 or 2 quick questions.
Yes. Yes, please go ahead.
And that data went into this machine learning model. Means
how many? So in the case of trapped vortex combustor from Professor Ravi Krishna's rig, we were able to get a time series of about 250 images. That was not sufficient to train the model. So what we went ahead, we just did LES simulations of those, generated more and more diverse data sets, and we also added noise to mimic the noise in the experiments, and we were able to train the model that gives reasonable accuracy for the predictions.
So you have used structured data?
Yes, structured data, yes.
So how many attributes?
So attributes means we have all the grid points, and at each grid point we have paired data of the OH mass fraction scaled to OH star chemiluminescence, and the outputs are the U and V components of velocity.
Okay.
Yeah. Yes.
Yeah, so the question is, as you have suggested the model for...
Mike.
Hello.
Yes.
Yeah, my question is, as you have suggested the ML model for using into the modeling approach, right?
Yes.
So suppose if I have a reaction mechanism of 2000 or 3000 reactions, okay?
Yes.
And in that, we also need to consider the abstraction and addition of H and OH atoms. So
Right.
how this model is, will this model be able to help in that predictions? As well as, there is one more question. How about the stiffness of this solver? Like, if we go for different solvers, it has different stiffness. Like if we compare Converge, ANSYS, Chemkin. So,
right.
Yeah. So can you explain about that?
Right. So most of these commercial solvers, they do detailed chemical kinetics in some form. What we use are our own custom solvers which do fully resolved chemistry. We go to a time scale of about 5 nanoseconds if required and 1 nanosecond at high pressure. So what we resolve is much more detailed chemical kinetics than any of the commercial solvers, right? Next question is, what is required? It depends on at what fidelity you want your results. For engineering macro scale quantities, probably you don't need that fidelity. But once you understand some one-off case and you want to understand the fundamental physics of it, then you want to run these high fidelity calculations. Okay, so currently we are developing a framework where you exchange data between DNS to LES to RANS to 1D surrogate model with uncertainty quantification and error propagation. So we are developing the entire stack of exchanging information across different fidelities, and that will be able to answer your question. One last thing that I want to show you here is you are asking about the number of species and reactions, right? So here we use a graph. Okay, so this is not coming. Anyway, here we have developed a graph neural network based algorithm. So there is a Aramco mechanism or Curans mechanism that has about 1000 species. And now what we are able to do is, if I if my combustor works in a certain regime of equivalence ratio and temperature, we are able to fully optimize the entire chemistry only for that range and do the simulations only with that reduced mechanism. If you use DRG and all, they are more generic, they give much larger mechanisms, but with GNN based mechanism reduction that's currently ongoing, we are able to significantly reduce that, very specific to the simulation conditions. Okay.
Thank you.
Yeah, thank you.
Thank you, Aditya sir. I kindly invite Dr. Sridhar Tota, Professor in Department of Electronics, Alliance University, to do the honors of presenting the gift to Aditya sir. It is my pleasure to introduce our next speaker, Professor Sushoban Avasthi, a leading researcher in semiconductor device fabrication and photovoltaics at the Indian Institute of Science, Bangalore. Professor Avasthi has over 2 decades of experience in advanced solar cell technologies with a specialization in heterojunction and thin film photovoltaics. He earned his PhD from Princeton University, where his pioneering work focused on organic silicon heterojunction solar cells. He continued his research at the Princeton Institute for the Science and Technology of Materials, working on oxide or silicon interfaces for next generation solar devices. Since joining IISc in 2014, Professor Avasthi has been a faculty member at the Center for Nanoscience and Engineering, where his research group explores metal oxide electronics and scalable solar technologies. His work bridges fundamental materials sciences with real-world energy applications, contributing to India's clean energy mission. He also serves as chair of the Safety Committee, IISc, reflecting his commitment to responsible research practices. Please join me in welcoming Professor Sushoban Avasthi to share his insights with us today.
Professor Avasthi, you have 15 minutes of time.
Sure. So in that case, thank you all for the kind introduction. As you probably have noticed, I come from a slightly different background. I'm not trying to make hydrogen burn. I'm actually going the other direction. The reason I'm here is that as microfabrication as a sector uses a lot of hydrogen, and I am a consumer of hydrogen. And one of the things we worry about all the time is making sure hydrogen stays uncombusted. So this talk is mostly about hydrogen safety. Just a caveat, I'm not an industry veteran. Much of what I'm going to talk about is something I've read or learned or sort of imbibed as a practitioner or somebody who uses a lot of hydrogen every day. Okay. So the hydrogen hazards are well known. I mean, I just quickly searched. There were more than 4 or 5 accidents that have happened in India in the last 5 years. And whatever I'm going to talk about essentially has been captured fairly well. Hydrogen is one of those very well studied gases. If you look for data, you will find a lot of it in hydrogen. And BIS standards, which is what apply to India, largely follow the codes that are mentioned upstairs. Okay, so let's get to it. We're first going to deal with transports, storage, and infrastructure. I'll start with this. This is not nitrogen. This is not hydrogen. This is actually nitrogen, but I want to make a point. This is actually the incident report of a liquid nitrogen cylinder that exploded in University of Texas, Austin. I'll just read it out. The story is there was a cylinder. It has a safety release valve. The safety release valve went off. A student decided that that is not very necessary, so they replaced it with a plug. And then one night, the cylinder exploded. So this is what happened. Thankfully, nobody was in the lab, so it's funny, but it still makes the point. The cylinder was standing at one end of a 20 to 40 feet laboratory on the 2nd floor of the chemistry building. It was on a tile-covered 4 to 6 inches thick concrete floor directly over a reinforced concrete beam. The explosion blew all the tiles off the floor for a 5 feet radius around the tank, turning the floor tile into shrapnel that embedded themselves on the walls and doors of the lab. The blast cracked the floor, but due to the presence of the concrete beam which shattered, the floor held. Because the floor held, the force of the explosion was directed upwards and propelled the cylinder without the bottom through the ceiling into the mechanical room above. It struck through 2-inch bottom vanes and drove the electrical wiring above into the concrete roof of the building, cracking it. The cylinder came to rest on the 3rd floor, leaving a neat 20-inch diameter hole. In its wake, the entrance door and the walls of the building were blown out into the hallway. All the remaining walls of the lab were blown 4 to 8 inches off the foundations. Just imagine what that means. That means there is a room and it became bigger by 4 inches. And that is just nitrogen, right? As things go, it's rather innocuous, it's safe. The point is there's a lot of mechanical energy stored in the system, and that mechanical energy, if misused, can cause a lot of problems. And with hydrogen, the issue is on top of that mechanical energy is chemical energy. That's what makes hydrogen interesting to a first order. So largely there are 3 types of storages. You will have gas cylinders, you will have bulk cylinders, and you will have liquid hydrogen tank. That's, to my knowledge, the largest liquid hydrogen tank that's owned by NASA. I'll mostly talk about the first because that's what I understand the best. I'll talk a little bit about the middle. I'll have 1 or 2 slides on the last. So first, the general things that every cylinder you should follow. Make sure the cylinder stays vertical, make sure it has a valve cap, and when you are transporting it, make sure it is trapped. Simple stuff, but if you go on Bangalore roads, you will find that 80% of the time this is not followed. You're also not supposed to roll the cylinder. It looks very cool, but it's not actually safe. Definitely don't do that for hydrogen. You're always supposed to use carts. And again, basic hygiene, all cylinders must be labeled. I promise you, you go to any lab in the country, 80% of the time this is not followed. They're supposed to be restrained. Why? Because a fallen cylinder will crack and become a missile. And finally, you should segregate cylinders based on flammability and other considerations. The reason I'm going through this fast is because this is basic stuff, okay? None of this is, all of this is needed for hydrogen, and then you need to add the things I'm going to talk about, okay? So let's get this slide out of the way. This is what sets the tone. This is what makes hydrogen dangerous. So what is unique about hydrogen is, number one, the range of flammabilities or range of concentration where the thing can explode on you is fairly large. Much larger than any other fuel we use, for example, natural gas, propane, or gasoline. Okay. Specifically, it will go from 4% all the way to 75%. People instinctively and assume that gasoline is very flammable over a very large range, but the hydrogen is much more flammable over a much larger range. Then related to air, it is much lighter. That has consequences that it sort of diffuses up into corners and is very hard to pump out. If you put an exhaust fan in this room, air will get out. But if there's hydrogen in this room, there's a good chance it will not. And finally, it takes very little energy to actually create an explosion with hydrogen in terms of millijoules of energy. A gasoline vapor will sort of will start combust or exploding at around 0.2 millijoule. Hydrogen will do so an order of magnitude lower. To give you context, static electricity, what you get on winter time when touching a metal door is 1 millijoule. So significantly smaller fraction than that is enough to explode a hydrogen cylinder if you let it. Next bit, which is again something funny unless you see it, hydrogen flame is largely invisible. I have actually talked to somebody who has seen it, a hydrogen cylinder on fire, and they say the only reason we knew the hydrogen cylinder was on fire because you touched the outside of the metal container and it was hot. Hydrogen flame can sometimes be completely invisible, especially in daytime. And lastly, the wavefront of hydrogen moves extremely fast. This has consequences for how far you have to be before you are safe, because the wavefront moves very quickly to deflagration, not just, it moves very quickly to explosion. It is not just a ball of flame that is moving. Okay. So these are what makes hydrogen essentially dangerous. Now let's get to what that means in terms of practice and how to use it safely. Thankfully, one thing hydrogen does not have is toxicity. Those of you who work with hydrides, there are many hydrides which are also very toxic, but that's not the problem statement here. So largely toxicity as a hazard is not there. Okay. So what do you talk about? Ideally, you want hydrogen in an open space. You want it in a very ventilated space. There is nothing like a room where hydrogen should be stored. You should, of course, protect it from traffic. You should protect it from falling objects. Very important for India, the standards mention that it should not go above 52 degrees C, which for most parts of India on a concrete floor, under the hot sun in the summer is too high. That's one of the reasons in most places in India, open areas become a little tricky. Usually people will have some sort of a shed. If you do have a shed, then you have to think about it a little bit more carefully, because that means the hydrogen can then stay inside. And if it can stay inside and accumulate in corners, then it's a problem. So what people do is they either have a passive ventilation system, something like that, where you have an inlet and outlet, which is at least 0.3 meters square per 1 meter square volume, essentially ensuring that hydrogen dissipates before it accumulates. If you cannot have a passive ventilation system and you are looking for an active ventilation system, then the typical architecture of the AHU sitting on the top with exhaust fans on the side does not work with hydrogen. You have to fundamentally redesign it. The AHU needs to come from the bottom, the air needs to sort of rise up, and typically the roof is designed in a manner that the hydrogen escapes without getting stuck in crevasses. Okay. Then ideally you should never keep cylinders of different types together, but in research and others sometimes that's required. So even then there are certain minimum distances that must be between hydrogen and an oxidizing cylinder, and if you do have them in the same shed, there should be some barrier between them. In general, hydrogen detectors are mandatory, usually at 10% of the LEL. So that translates to around, give or take, 500 ppm. At least in our department and much of IISc, we have started, if you are keeping things indoor, you might as well keep them inside a gas cabinet. This is not required by law or required by regulations, but it's a good practice for a simple reason that even if the detector detects a hydrogen leak, what can you do? What the gas cabinet essentially does is it contains the hazard into a cabinet. So sure, the rest of the area is safe, because otherwise you detect a gas leak, what do? You just evacuate and then wait for the hydrogen to dissipate. So a gas cylinder is usually a good idea, especially in close to population, small areas. Hydrogen embrittlement is a real problem. Many of you are from material science and mechanical domains, you probably know it better than me. But the basic idea is hydrogen permeates into a metal and over a period of time reduces its ductility, and very hard steels tend to crack. This has consequence for both the plumbing that you do for the hydrogen, but also for the cylinders that you use for the hydrogen. Ideally, you should only get cylinders that are rated for hydrogen to be stored for long term. Normally, those are authentic stainless steels or aluminum alloys or nickel-based super alloys. High strength steels with more than 1 gigapascal of yield strength are typically very bad. What that means in terms of practice is typically if you have a type 1, type 2 cylinder, which translates to if you have a metal cylinder, usually you should get it hydrostatically tested every 5 years. That is what PESO requires. And in general, after 10 years, I would recommend just change it completely. Don't keep it. You never know, these things have huge consequences. Coming back to the piping network, largely hydrogen, because again it's so light, it is so dense, it diffuses so quickly, you typically don't want to have threaded joints anywhere. The whole piping network is typically completely welded. There are certain compressed fittings like swage lock and Lore lock and all of those that are rated for hydrogen and you can use them. But as much as possible, have completely sealed lines everywhere. Some places even recommend, I know for example Shell does this, Shell even recommends to use coaxial tubes. What coaxial tubes basically are, there is an inner tube which is made of steel and then there's an outer tube made of steel, and between those two layers is either vacuum or an inert gas. So if the first thing leaks, the other one will not. Okay. Sorry, that is that. So let's quickly move liquid nitrogen. Maybe I'll just move this. I will. Okay. This is the part. Many of you, I was looking through the presentation, many of you work on combustion. If there is combustion, you typically want to have flashback arresters. Usually for hydrogen, 2 are recommended, one at the near the cylinder and one at the point of use where the combustion actually happens. Because of the very small amount of spark that it takes to actually cause combustion in hydrogen, usually hydrogen cylinders are earthed. This is a very common mistake that many people do. They don't earth their cylinders. It should be always earthed. You should ideally have explosion-proof fittings. Normal CFL lamps, tube lights, LED lights, they all have arcing possibilities and they are not recommended where hydrogens are used and stored. In fact, really serious people, for example, Shell would even use non-arcing tools that will not spark if dropped on the floor or if if you hit it with impact. Finally, emergency response. Liquid hydrogen is often used whenever you use massive volumes of hydrogen. The good thing with liquid hydrogen is you can store a lot of it. The other good thing about it is the leak is very visible. So if the leak happens, it actually causes this white smoke because water condenses. It's a very easy and very visible way of figuring out that there is a leak. But for hydrogen that is in the gas form, you don't have that advantage. So largely to a first order, flames are invisible. That means infrared detectors are mandatory. In fact, on hydrogen filling stations, you need flame detectors that can detect it. Normally there are suppression systems. Sprinklers are the usual ones that are always there. Some people add deluge systems near mass storage and fire suppression system. I was looking at Ravi's presentation and they have a fire suppression system in their hydrogen. Finally, this is my last slide, 1 minute. Of course, hydrogen holds a lot of energy, right? I mean, that's why it's interesting. So I'll just give an example of a 16-cylinder pallet. It essentially has around 2 gigajoules of energy, which translates around 500 kgs of TNT. That's a very big bomb that can go off. So ideally, wherever you put your hydrogen, the population should be a little bit away from it. So there are calculations you can do. These calculations were originally actually done for nuclear bomb experiments because they were exploding things and they wanted to figure out what's the safe distance. It turns out that same mathematics actually also applies for any explosion event. So what these are, okay, fine, you have 2 gigajoules of energy. What is the radius I need to go out before the pressure wave will dissipate enough that it is safe? So normally 1 psi is considered the standard. So if you run the numbers for 2 gigajoule, that distance is either 12 meters or 120 meters depending upon how fast the wavefront moves. And because hydrogen tends to explode, this is the one that is considered safe. So 12 and 120 is a huge difference. And that is why you typically draw these circles that if you're having a lot of hydrogen in one point, you should ideally house your office buildings that distance away. All right, that's all I have. Finally, incident reports. Hydrogen actually has very good incident reporting systems. If you want to know all the mistakes people have committed, you can actually go to these links and read them up. Because people who cannot learn from history are doomed to repeat it. I will leave you with this series of big images, and thank you for your time.
Thank you, Professor. Questions maybe we can take up in the lunch time. I'm sorry.
Thank you.
Thank you.
Thank you, Avasthi sir. I now invite Dr. Vivek Misra, Program Coordinator of PhD, Alliance School of Sciences, to present a small gift to Professor Avasthi.
So we have come to the close of this two-day national workshop on hydrogen fuel technologies and future trends. And it is a pride moment and gratitude to reflect our journey for these 2 days. So over the past 2 days, we have witnessed thought-provoking lectures covering all the spectrum of hydrogen technologies, from its role of internal combustion engines, gas turbines, and propulsion systems to safety aspects, and AI-driven design and future policy frameworks. Now, I invite Dr. V.K. Saraswat sir to give the closing remarks. Please.
First, I would like to say I'm the wrong person to give the closing remark because I have not attended all the talks which happened in the last 2 days. So if I'm going to talk to you now as a closing remark, it will be a very depleted version of what it ought to have been. The right person is, I think, Pandeyji or somebody who has been privy to all the talks. But from the spread what I have read out, the kind of talks which were planned, and I hope all of them have been given, I think this conference, this workshop has covered practically every aspect of hydrogen technology. As I mentioned in the morning, hydrogen is the future. It's a fuel which will change the style in all domains, whether it is power production, it is mobility, or it is in terms of addition to the economic value as far as the systems are concerned. Ultimately, it is the one which is going to help us to achieve the climate goals. Because we are looking at net carbon zero, we are looking at mobility without any production of greenhouse gases. We are looking at an industry which is decarbonized, and the only fuel which can decarbonize the industry is hydrogen. We have been working with various departments, particularly the steel departments, to switch over from coal and coke to hydrogen. They should use it as a reduction medium. You have already heard how much hydrogen can be used in the area of mobility, whether you use it as an IC engine or use it as a fuel cell. But the talks have covered all aspects. Talks have covered hydrogen production methods, talks have covered hydrogen storage systems, talks have covered how hydrogen will be used in IC engines, what are the kind of combustion processes which are involved, how do we can improve the efficiency, how hydrogen can be used in the fuel cells, and how hydrogen can certainly be stored and produced and taken for dispensation in various stations. So every aspect has been covered. As I mentioned day before yesterday, the learnings on hydrogen have come due to the rocket technology, most of it. Hydrogen came as one of the preferred fuels in the space and rocketry, and because of the fact that it is highly energetic, it provides the highest specific impulse. So people learned all about it. And from there it has now become a common word. In fact, there was a gentleman who said, "Can I produce hydrogen at home? Can you talk about supply chain?" I was amazed to listen that question. That is the kind of a perception people are having. So it is something which we have to work on. This workshop has also given lots of areas where research is required to be done. I try to highlight some of the areas where research is required to be done in my talk today. I am sure the other professors also, like Professor Morgan, Professor Ravi Krishna, Dr. Chari, all of them who are presently working. Dr. Chari is working on rotating detonation engine, which is going to use hydrogen as a fuel. So you will see how the detonation characteristics are there, how the flame speeds will be controlling that part of a detonation and things like that. He will be doing. We are all talking of different kinds of IC engines, and some innovations are required for making hydrogen as one of the most efficient IC engine fuel. Just after his talk, Ravi Krishna gave me a presentation on what are the new dimensions of a pre-combustion chamber or pre-ignition chamber, things like that are being done. Now we need to do more research, because we know hydrogen and oxygen, if I burn as a flame, it will burn and it will release some heat. That is not a problem. But we have to run it in the most efficient manner. We have to make it most cost competitive and so on. For that, the processes involved are important. The entire process of hydrogen combustion, which involves the chemistry. I mentioned to you about the combustion chemistry in my day before yesterday's talk. We have to model the turbulence. We have to model how the combustion is taking place, how the flame propagation is taking place in the combustion chamber, and which will be responsible for whether it's a deflagration process or a detonation process, how the turbulence and eddies are getting formed, which will improve the thermal efficiency. Now these are the areas where a lot of work is required to be done. Then the easiest path is, because ultimately we have to also look at how fast we can enter into this field. So easiest path is, can we modify the existing diesel engines or the petrol engines? with minimum modifications. So that is one priority I would set for all the industry partners and researchers, that you should be able to look at whether you go for port injection or you go for direct injection. You should be able to decide by way of experimentation as well as by modeling, CFD. All these studies have to be done to arrive at the right configuration. Ultimately, the challenges which I mentioned in my talk, and I'm sure many of you also aired the similar views, they have to be addressed, whether it is a NOx formation, or it is a pre-ignition taking place, or the backfire, or the safeties which are required in the handling of hydrogen, which our professor just now mentioned from ISC, the various aspects. I think each one of them have to be researched. So the team here should identify from these talks which have happened, the various areas in which research is required to be done. And I want that research not only limited to maybe publishing a paper. That should be done. I'm not stopping you from publishing the paper, but that paper should also get translated in the form of a product, in the form of a design, which will ultimately go to the industry for manufacturing. If it doesn't happen, then you will generate knowledge, but knowledge is only for the purpose of, sorry to use that word, self-glorification, but not for the economic growth. So translation has to be done, and translation can come only if you convert it into a product. If you are going to design a pre-ignition chamber, you design, optimize, you take a patent. You take a patent on that. If you are designing an injector for that, for direct injection, which I was talking, 500 bars or 300 bars if you are going to inject direct. So that injector which is going to work at that. Or even for that matter, a hydrogen pump which is going to compress for that injection, and that also has to be designed, developed, patented and manufactured. So every component which is there in this hydrogen system for IC engines needs that kind of a rigor, that kind of an analysis and that kind of a research for understanding, for translation and also for manufacturing by the industry. So that is the work, that is a journey you people, all of us together have to perform. Otherwise, we will continue in the mode of importing the devices from outside. I mentioned to you that there are companies like Westport, there are companies like Bosch, there are companies like Lucas. Many of them are already working on different kinds of components for hydrogen. There are companies in US and Japan who have already developed high pressure hydrogen compressors, which are ready to pressurize hydrogen to 700 bars and things like that. Now, why is it that we cannot start a program? Doesn't matter, even if it is a repetition, because it is not available. Even if it is available, it is so costly that we can't afford it. So can we think of designing a compressor here? Can we think of designing a hydrogen compressor here? Can a team from Alliance University, IASC and some other organizations pool together their brain and work with the industry and design a hydrogen compressor? So that is the kind of message I would like to deliver. I would like that you should get into the mode of translation. Otherwise, we will remain in that mode. I was very happy to see that the present day technologies are being used today for manufacturing the parts of the IC engines. Ravi showed a combustion chamber which is manufactured on the 3D printing. There are companies today manufacturing a full rocket engines by 3D printing. There are startup companies, they are doing that. So that going into the domain of the new technologies is very important. Similarly, when you are going to do the research, the new tools which are emerging, which are AI assisted tools, the CFD what you would have probably used in 1995 or 2005, probably if it is now assisted with the AI which is going to help it in reducing your burden for extracting the data or analyzing the data or making better predictions, why not we implement that? So don't remain in the domain of what I did in my journey. My journey is very old now, but your journey should be with the new technologies. So all these problems should be integrated with the new technologies and solutions to be found with them. For example, I was talking to your good name? Doctor. So he showed me boron. Now we were working on boron and we found boron was not a very pliable material. But he is able to innovate and he is able to say that I am able to burn boron. The problem of boron oxide I am able to solve. He is using artificial intelligence for doing the CFD of his rocket plume and things like that. So that is a kind of an approach you have to follow for doing the research in the hydrogen-based IC engines, hydrogen-based other devices. IC engine was the prime focus in this particular conference, but I think the fuel cell cannot be ignored. The fuel cell also should be worked upon. I mentioned to you in my talk that the efficiency of fuel cells are limiting to 45 to 50%. I think we have to improve that. So different kind of fuel cells and the dependency of noble materials and certain critical materials like Nafion for the membrane, we have to address that. We have to do research and create our own Nafion. Instead of using platinum or ruthenium as the catalyst or the coatings, can we think of some other materials so that they are low-cost materials? So even the fuel cell research requires different dimensions. The research which is going to help in the fuel cell area is the development of solid oxide fuel cells. And the solid oxide fuel cell theoretical studies show that it can give you efficiencies as high as 74%. So the work should be done on developing solid oxide fuel cell. And solid oxide fuel cell, the input materials can be methane, it can be methanol, it can be water and methanol. Various combinations are possible, but you have to learn how to operate those systems at high temperature, because solid oxide fuel cells work at about 800 degrees and so on. So people get scared, no, it's a very high temperature system. No, but we have to learn how to do it. Don't get suppressed by that. We should be able to do that. Similarly, I talked about making reformer for hydrogen, so that we can produce onboard hydrogen. Whether it's on an aircraft or it's on a truck, why can't you do that? People are talking of use of hydrogen in aviation. Now many people have worked upon gas turbines where they are working on hydrogen for aviation. I am saying that why not use hydrogen route for producing the methanol, hydrogen route for producing the sustainable aviation fuel, and combination of hydrogen with the SAF. Like we are doing HCNG, can we talk of H plus the SAF together and make use of that? So there are various options possible. The research has to be done in these areas. And since we are at Alliance University, since we are in Bangalore, where most of the prestigious academic institutions and industries are available, there can't be a better place than Bangalore to create a cluster of researchers who will solve, if not all the problems, but some of the problems which are related to hydrogen. I have already requested Mr. Pandey and all other my team from Combustion Institute to jot down the outcome of this particular conference, identify the areas in which actionable R&D has to start, what are the areas where we have to work with industry for productization of the various devices which are getting developed here, and work with the OEMs for using the low-hanging fruit of modifying the existing IC engines for application in the hydrogen. So this is the kind of a roadmap I would like to lay. I certainly take this opportunity on behalf of CII to thank you all for being part of this workshop. Particularly thank Alliance University, the Vice Chancellor, the Pro-Chancellor. Yesterday I made a mistake, I called him Pro-Vice Chancellor, my apologies for that. So all of you and all the staff which has made this particular conference very successful. In fact, I am very happy that even on the second day, we have almost same attendance as was on the first day. That only shows the interest which has been evoked in this particular conference. Wish you all the best in your research in the future and let the country benefit by your efforts. Good God bless you. Namaskar.
So all of you have heard the final closing remarks from Dr. V.K. Saraswat, right? I was just trying to see how it started. You called me, sir, on 22nd July at 10:30. I'm seeing the WhatsApp. And that time you were driving to office and I was in front of my laptop. I had a pen and pencils, whatever. So you gave me 13 points like a missile. You are a missile man, so you are firing like a missile, 13 points. And I just started noting down like this. And you started to talk to Ravi Krishna. I did not even lose the time to type it. The same thing, whatever I chalked down with the pen and pencil, I forwarded to me exactly same minute. Not even a minute was lost. And Ravi Krishna was so kind enough to really say, yes, we'll do it. And then I communicated to you, yes, it's going to happen. So 13 points given by boss communicated to Ravi Krishna. And from there onward, the journey started. Then we spoke to Alliance University. Thanks to Professor San. He was so gracious and enthusiastic to say, yes, we'll host it. Even though Ravi Krishna himself was ready to host in School of Science, but we thought, okay, let's create some other cluster of hydrogen fuel in Bangalore. So thanks to you, Professor San, for coming forward. And where are you, Professor San? Oh, so thank you for coming forward and taking this challenge. So all 13 points have been covered, thankfully, today. After that, I think we started working on this. So how much work has gone? Only I think 3% knows typically me, Dr. Sheila, right, Dr. Sheila, Sheila, and Professor San, of course, and Dr. Hasim. So these are the only 4 persons we converted. And of course, Ravi Krishna, thank you for taking the call at very odd time. We were on vacation for almost like 10 days. And I don't think that you enjoyed the vacation. So sorry about it, because you were in some place with your family and I was calling you every 1 hour and I was feeling personally guilty that I'm irritating you because you are on personal vacation, but there was no time because it was all in July end, right? So thankfully the things have been done. So now the going forward plan from here is that we have, as Sir said, that we are making a note of all the actionable. We are going to compile all the actions, whatever we have thought about from our level. And then Professor Ravi Krishna, again, I will be coming back to you again with the leadership to form a team and review this actionable. And after that, we will have one panel discussion in Delhi or somewhere where Dr. Saraswati is available. We'll have a panel discussion with the industry and academia to make sure that all the four ends, all the loose ends has been tied. And from there onward, maybe 20, 25 actionable or the topic will identify, which can be thrown open across the country. It can be worked as a project of MTech or, the research scholars or PhD. And from there onward, we'll try to combine this with Dr. V.K. Saraswat's vision of how to tie this with the final goal of Prime Minister. So that is the game plan. So I will come back to you. So this is only 1/3 of the work is done. 2/3 work is still there. So thank you, Professor San, again for helping me with all the AI generated, that whatever you guys are talking, it is getting generated in text. So don't be surprised that, a lot of things what you spoke has been covered. But, we have to review whether it really has been captured to the extent what it should be. So once we review internally, it will be formulated in a document. And then Professor Ravi Krishna, you have to take off from there. And then the panel discussion and the final goal is to identify the topic and throw open for work. So thank you so much, everyone. Thank you.
So we have come to the closure of the two-day workshop. And on behalf of Alliance University, IISc Bangalore, and CIS, we extend our heartfelt thanks to all the speakers, participants who have come and joined here and made it as a resounding success. Thank you all. I request everyone to kindly rise for the national anthem.
शुभाशिष मांगे
Yeah, I request all the delegates to kindly assemble in the faculty lounge ground floor. And for the participants, you can collect your certificates in the RTM in ground floor, and then you can move for the lunch in the first floor food court.
Sorry, we have arranged a tree plantation drive for all the people who have come over here. So before going for lunch, we'll just guide you towards the place where we have got the tree plantation drive. One full corridor we have taken. We'd like to name that corridor on behalf of the workshop that you have got this time. So join us for the tree plantation drive, and then we'll go for the lunch and we'll part. The feedback will be collected from everyone through Combustion Institute. We'll send a form to everyone. We'll record your feedback, and if there is anything that has let you down, please let us know. We'll try to improve next time. Thank you.
So delegates kindly come to the faculty lounge. We'll all start from there together for the plantation.
Thank you so much. Thank you. Madam Sheila, thank you.